Hello there and welcome to Just About Earth, where we take a calm look at the planet beneath our feet, the history hidden within it, and the questions that remain unsettled, even after people have measured, photographed, mapped, and argued about them for years. Tonight we are travelling to the mountains of southwestern Montana, where an unusual granite formation has become the centre of a growing dispute. Some visitors believe they are looking at the remains of an enormous prehistoric structure. Others see a natural rock exposure shaped by cooling, cracking, uplift, frost, water, and erosion. The formation is known as the Sage Wall, and depending on who is describing it, it is either one of the most important archaeological discoveries in North America or a particularly convincing example of geology being mistaken for architecture. It is also possible that neither description is completely fair, because before anyone can identify who built a structure, they first have to establish that a structure was built at all. The Sage Wall is located on private property at the Sage Mountain Centre near Whitehall, Montana. The owners say they encountered it while walking the land in 1996, although it took many years before photographs and videos brought the formation to a wider audience. They describe the visible wall as approximately 275 feet long and up to 24 feet high, with sections formed from massive blocks of granite divided by prominent seams. The site lies within the boulder batholith, a huge body of igneous rock that stretches across a large part of southwestern Montana. A batholith forms when magma rises into the crust, cools below the surface, and eventually becomes exposed after the material above it is removed by erosion. The boulder batholith is dominated by granite and closely related rocks, and scientific dating places much of its formation in the late Cretaceous, roughly 70 to 80 million years ago. This means the stone itself is not mysterious in origin. The mystery concerns the shape it has taken and whether human hands had anything to do with that shape. Before we move closer, I would love to know where you are listening from tonight and whether there is a place near you that people cannot quite explain. Perhaps there is an old stone wall disappearing into a forest, a line of boulders crossing a hillside, a strange mound beside a road, or a local ruin that has gathered several different histories. Maybe everyone in your town agrees about who made it, or perhaps every person tells the story differently. Places like that often become more than physical objects. They collect memories, guesses, warnings, family stories, and confident explanations offered by people who have never actually visited them. Sage Wall has begun to gather that kind of reputation. It has become a place where visitors arrive carrying ideas about ancient technology, lost civilizations, forgotten migrations, natural forces, institutional resistance, and the limits of accepted history. The granite does not comment on any of this. It simply remains where it is while people examine its cracks. If you find these quiet investigations soothing, or if you enjoy mysteries that are allowed to remain uncertain until the evidence is properly considered, I would be grateful if you gave the video a like and subscribe to Just About Earth. It helps this small corner of calm reach other people who might enjoy learning about unusual places without being told what they must believe before the investigation has even begun. There is no need to decide immediately whether Sage Wall is a monument or a mountain. We can look at what is actually present, examine the major claims, compare them with known geological processes, and see which questions can be answered. There may also be questions that cannot yet be answered, which is not a failure. Sometimes the most accurate conclusion is that the available evidence is incomplete. That is less exciting than announcing a lost civilization, but it is usually more useful. The first photographs of Sage Wall can create a strong impression. Large pale blocks appear to sit beside or above one another. Dark lines run between them, sometimes horizontally and sometimes vertically. Certain faces seem flat. Some corners appear unusually sharp. A few sections look as though they might belong to courses of masonry rather than a single body of fractured rock. When a person stands beside the formation, the blocks seem much larger than they appear in isolated photographs. This sense of scale is important because large objects affect judgment. A small rectangular stone is easy to accept as the result of a crack. A rectangular mass weighing many tons encourages the mind to imagine cranes, ropes, ramps, workers, and a reason for placing it there. The larger the block appears, the more intentional the formation can feel, even though natural forces routinely move, fracture, expose, and separate masses far beyond anything human beings could lift. The setting changes the impression once the camera turns away from the wall. Sage Wall is not an isolated object standing alone on an empty plain. It is surrounded by the varied granite terrain of the boulder batholith. Rounded boulders, broken outcrops, exposed faces, mineral veins, and intersecting fractures occur throughout the region. The University of Montana describes the landscape as being characterized by rounded boulders produced through the weathering of fractured granite and quartz monzonite. The magma that formed the batholith cooled beneath the surface, creating cracks and fissures. Later, erosion removed the overlying material and exposed the rock. Some fissures in the wider batholith became channels for mineral-rich fluids and can extend for great distances. In other words, long cracks, large blocks, repeated fracture directions, and unusual stone shapes already belong to the known geology of southwestern Montana. That does not explain every feature at Sage Wall automatically, but it establishes that the formation exists in a landscape capable of producing large and organised-looking patterns without construction. This is where the discussion becomes difficult, because people tend to approach the wall through two very different stories. The first story begins with a lost culture. According to this view, the visible granite is part of an ancient megalithic complex built by people whose technology and history have disappeared. The wall may once have been taller or longer. Much of it may remain buried beneath soil and fallen material. The large polygonal blocks may have been cut, fitted, and placed with methods that are no longer understood. Projecting knobs and cup-shaped marks may have served practical or ceremonial purposes. The alignment may have been chosen in relation to the winter solstice. Unusual magnetic readings may indicate that the builder selected particular stone or understood properties that modern researchers have overlooked. The absence of familiar artifacts is explained by age, erosion, burial, limited excavation, or the possibility that the builders belong to a culture not yet recognised by archaeology. The second story begins inside the rock. In that view, Sage Wall is a natural exposure of ancient intrusive stone that fractured along existing weaknesses. Pressure was released as the material above it eroded. Water entered cracks. Repeated freezing expanded those cracks. Chemical weathering altered some minerals more quickly than others. Soil formed, roots grew, fragments loosened, and gravity removed unsupported material. Intersecting joint sets divided the granite into large blocks. Some blocks remained attached to the underlying mass, while others shifted slightly, creating gaps that resemble masonry joints. Different rates of weathering produced rounded projections, shallow hollows, flat surfaces, and darker seams. From the correct angle, one exposed portion appears remarkably straight, but the shape becomes less regular when the wider outcrop and surrounding terrain are included. Both stories can be made to sound convincing when presented alone. A close photograph of fitted-looking blocks supports the construction story. A wide photograph of fractured granite supports the geological story. A visitor pointing to a straight seam may ask how nature could possibly make it. A geologist can answer that rocks often split along repeated planes. The visitor may then point to another feature that does not seem covered by that explanation. The geologist may request a mineral sample, a detailed map, and several weeks of fieldwork. By then, the short online video has already ended, and the comments are busy selecting a winner. The problem is not that people are curious. Curiosity is exactly what a place like Sage Wall deserves. The problem begins when appearance is treated as proof. Human beings are highly sensitive to order. We recognise faces in tree bark, animals in clouds, letters in cracks, and familiar objects in shadows. This ability is essential to ordinary life, but it also means that once we begin seeing blocks in an outcrop, the rest of the formation may start arranging itself in our perception. Every horizontal line becomes a course, every vertical fracture becomes a joint between stones, every protrusion becomes a lifting boss, every hollow becomes a tool mark. Evidence that does not fit the pattern may receive less attention because the mind has already decided what kind of object it is examining. Geologists are not immune to expectation either. Someone who has spent a career studying natural granite weathering may look at Sage Wall and recognise familiar forms immediately. That recognition can be accurate, but familiarity can also encourage a quick conclusion. Saying that granite commonly fractures does not explain the precise geometry of a particular outcrop. A proper geological explanation would need to examine the directions of the joints, the mineral composition, the relationship between visible blocks and underlying bedrock, the effects of local slope movement, the history of weathering, and whether similar patterns appear nearby. The natural explanation should account for the unusual details rather than dismiss them simply because natural rock formations are common. The same standard must be applied to the construction claim. If Sage Wall was built, there should be physical evidence of building. Researchers would look for repeated marks caused by tools, surfaces that were deliberately dressed, stone chips produced during shaping, quarry locations, transport routes, packing material between blocks, foundations placed into prepared ground, and archaeological deposits associated with the people who carried out the work. They might find hearths, charcoal, bone, tools, pottery, fibres, food remains, or other traces of human presence. Even a structure built without pottery or metal should leave some sign of the activities required to plan, shape, move, and assemble enormous masses of stone. A convincing theory would also need to explain the original function of the wall and why builders selected that location. No accepted body of archaeological evidence currently identifies Sage Wall as a prehistoric structure, provides a construction date, or links it to a known culture. The owners of the property present the site as an open mystery and have described a range of investigations, including surface mapping and non-invasive surveys. But the publicly available material does not establish that the granite blocks were quarried and assembled by human beings. The absence of proof does not demonstrate that no human modification occurred, but it means claims of a vast megalithic complex remain unconfirmed. The title of our investigation therefore contains a useful trap. Asking who built the wall assumes that the wall had builders. The first question must be whether the evidence supports construction in the first place. This distinction may feel overly cautious, especially when the formation looks so striking, but archaeology depends on context. A stone can be natural while the place around it was used by people. A natural cliff may contain carvings. A cave may become a shelter. A ridge may mark a boundary. A boulder may serve as a landmark, a gathering place, or part of a seasonal route. It is therefore possible that Sage Wall is naturally formed and still has an unknown human history. People could have visited it, marked it, cleared parts of it, placed smaller stones nearby, or incorporated it into activities that have left faint traces. The choice is not limited to a completely artificial monument or a place never touched by human beings. There is also the possibility that the formation has changed significantly since any human interaction occurred. Montana's climate, vegetation, and surface conditions have not remained fixed. Soil can build up against rock, frost can widen cracks, trees can grow and fall, water can remove sediment from one area and deposit it in another. A section that appears buried may simply continue naturally beneath the slope, although a deliberately buried foundation could create a similar appearance. Without controlled investigation, the same observation can support opposing interpretations. That is why features below the surface have attracted so much interest. The site's supporters have discussed ground-penetrating radar, electromagnetic measurements, LIDAR mapping, mineral studies, and other non-invasive techniques. These methods can be valuable, but their results require careful interpretation. Ground-penetrating radar does not produce a direct photograph of underground architecture. It records reflections caused when signals encounter changes in material. Rock boundaries, moisture, roots, sediment, voids, and buried objects can all produce responses. LIDAR can create a precise map of surface shape and reveal alignments hidden by vegetation, but it cannot determine whether those alignments were designed. Magnetic measurements can detect differences in the rock, yet granite commonly contains minerals capable of influencing a magnetic instrument. None of these observations becomes archaeological evidence merely because the instrument produces an unusual reading. A strong investigation would combine methods. Geological mapping could show whether the apparent blocks follow natural joint directions. Petrographic analysis could identify whether stones that appear separate share the same mineral structure and cooling history. Microscopic examination could distinguish fresh breaks, weathered surfaces, and possible impact marks. Archaeological survey could look for cultural material in undisturbed contexts. Carefully placed trenches, if permitted and justified, could reveal whether the formation rests on prepared ground, continues as solid bedrock, or includes deposited blocks. Samples associated with human activity could potentially be dated. Measurements of the wall's alignment could be compared with the local topography and the actual position of the solstice sunrise. The results should then be published in enough detail for independent specialists to evaluate them. Until work of that kind produces a clear result, Sage Wall remains suspended between visual impression and demonstrated explanation. This is not as unusual as it sounds. Many disputed formations exist because natural processes sometimes create shapes associated with construction. The more geometric the result, the more difficult it becomes to accept that no one planned it. Yet geometry is not owned by human beings. Crystal structure, cooling stress, gravity and erosion can generate repetition without intention. Snowflakes have symmetry without designers measuring each branch. Basalt can form columns without masons. Mud can dry into polygons without surveyors. Granite can split along intersecting planes without anyone drawing a line on it first. The question is whether the particular order at Sage Wall exceeds what those processes can reasonably produce. That cannot be answered by saying that nature is capable of remarkable things, because capability alone does not explain a specific case. It also cannot be answered by comparing the wall with famous ancient sites and noting that both contain large stones. Similar appearance does not establish a shared origin. Granite outcrops in Montana, polygonal masonry in South America, stone platforms in the Pacific, and temple walls in the Mediterranean each belong to different geological and archaeological settings. Comparisons can suggest features worth examining, but they cannot replace local evidence. This is especially important when discussions of Sage Wall move toward unknown advanced civilizations. An extraordinary ancient culture is not impossible merely because it would surprise us. Archaeology has repeatedly expanded its understanding when new sites, dates, and technologies were discovered. Human beings have organized large workforces, moved heavy stones, observed the sky, and constructed durable monuments for thousands of years. The issue is not whether ancient people were intelligent enough. They clearly were. The issue is whether evidence connects such activity to this place. Respect for ancient capability should not require us to label every unusual stone formation as a forgotten city. There is a quieter reason the site attracts people. A human-built Sage Wall would add an unexpected history to a landscape already carrying an immense geological one. The granite began as molten material deep within the crust during a time when dinosaurs still lived. It cooled over millions of years within a large and complicated intrusive system. The rocks above it were gradually removed. Fractures opened, minerals changed. Individual blocks emerged from a buried mass. Much later, people arrived in the region and encountered a landscape shaped by processes they could not see happening. Whether anyone altered this particular outcrop or not, its known history already covers a span almost impossible to imagine. USGS research describes the boulder batholith as a composite group of intrusions rather than a single simple body. with major phases of magmatism occurring during the late Cretaceous. Its origin involved repeated emplacement, chemical variation, crustal structures, and long cooling histories. Sage Wall therefore stands within a geological system far more complex than the word wall suggests. Yet a geological history does not satisfy the same part of the mind as a human story. Magma has no name. Erosion leaves no inscription. A prehistoric builder gives us someone to imagine. We picture people standing in the same place, making decisions, solving problems, sharing instructions, and watching the structure rise. We ask what they believed, where they came from, and why their work was forgotten. A natural formation offers no lost architect, only physical processes operating without intention. That may be one reason the artificial explanation feels more complete even before the evidence is complete. For tonight, there is no need to remove that possibility. We only need to hold it carefully. Sage Wall might be entirely natural. It might include human modification that has not yet been demonstrated. It might preserve evidence that future investigation will interpret differently. What it cannot honestly be called at present is a confirmed prehistoric megalithic complex with known builders. The available information does not support that conclusion. It supports a more modest and more useful statement. A large granite formation in Montana displays features that some observers interpret as construction, while the established geology of the surrounding region provides plausible mechanisms for producing large blocks, long fractures, and architectural-looking forms. As you imagine standing in front of it, consider what would persuade you. Would a perfectly straight alignment be enough, or would you need tool marks? Would an underground continuation suggest a foundation, or simply bedrock? Would a winter-solstice orientation demonstrate planning, or could it occur by chance in a landscape full of ridges and sightlines? If a compass behaved strangely beside one block, would that indicate technology, or a concentration of magnetic minerals? These are not questions with equal evidential weight, but each one has become part of the Sage Wall story. The most sensible place to begin is with the physical impression that started the argument. Before the magnetic measurements, before the solstice claims, before speculation about buried complexes and vanished builders, there were the stones themselves. They appear enormous. Several have polygonal outlines. Some seams look narrow and deliberate. Portions of the exposed face seem to follow a straight course for a considerable distance. To understand why the formation has been compared with megalithic masonry, we must move close enough to examine those blocks, then step back far enough to see whether their apparent order continues through the surrounding rock. Approaching Sage Wall from the trail, the first thing that changes is the sense of scale. Photographs can show the seams, the pale granite, and the dark lines between the larger masses, but they do not always show what it feels like to stand beneath stone that rises well above a person. The property owners describe the exposed formation as roughly 275 feet long and reaching about 24 feet in height in some places. Across that distance, the rock is divided into large sections with flat-looking faces, intersecting edges and gaps that can resemble the joints between separate pieces of masonry. A single, unusual boulder might be easy to dismiss as an accident of erosion. A long row of them encourages a different reaction. The eye begins following the line from one end to the other, checking whether one block appears to rest on the next and whether the seams continue in a pattern. Before long, a natural outcrop can begin to look like the surviving face of a structure whose upper courses have fallen away. That visual effect is the foundation of nearly every extraordinary claim made about Sage Wall. The blocks do not all have the same shape. Some appear roughly rectangular, while others have 4, 5 or more visible sides. Certain edges meet at angles that look fitted rather than broken. In photographs taken from favourable positions, narrow seams seem to separate one mass from another with surprisingly little empty space. Supporters of the construction theory compare these shapes with polygonal masonry, a method in which large stones are worked into irregular forms and fitted together without relying on uniform rectangular bricks. Famous examples of polygonal construction are found in several parts of the world, and the technique can produce walls that remain stable because the varied joints distribute forces through many directions. When people see similar-looking outlines at Sage Wall, it is understandable that they ask whether the granite was shaped according to the same general principle. Similarity, however, is the beginning of a comparison rather than the end of one. Two walls may share a visual pattern while having completely different origins. One may consist of quarried blocks placed by builders, while the other may be a continuous body of rock divided by natural fractures. From the front, the difference may not be obvious. If a fracture enters the stone at an angle and meets another fracture below the surface, the exposed section can resemble a fitted polygon. If weathering widens the crack, a dark line appears around the apparent block. Soil, moisture, lichen, and shadow can deepen that line, making the stone look more separate than it really is. A photograph records the surface contrast but does not show whether the apparent block continues into the bedrock behind it. This is one of the first things a detailed geological investigation would need to determine. A built wall is assembled from separate units, even if those units are enormous. A fractured outcrop can look assembled while remaining part of one continuous mass. To distinguish between them, researchers would examine where the seams lead, whether they close beneath the surface, and whether the mineral grains continue across the apparent boundary. If two faces were once joined and later split, matching minerals and textures may appear on both sides. If one stone was transported and placed beside another, the relationship could be different. Weathering complicates the comparison because exposed surfaces change over time, but the internal structure of the rock can still preserve information that appearance alone does not provide. The regional geology makes natural fracturing a serious explanation rather than a convenient excuse. Sage Wall lies within the boulder batholith, a large group of late Cretaceous intrusive rocks dominated by the Butte granite and accompanied by several related intrusions. These rocks contain quartz, feldspars, biotite, hornblende, and other minerals in varying proportions. They did not form as loose blocks at the surface. They cooled from magma within the crust and were later exposed as overlying material was removed. The process created a large solid rock body, but solid does not mean unbroken. Cooling, pressure changes, tectonic stress, and later movement produced joints and faults throughout the region. USGS mapping of parts of the batholith records multiple fracture and fault directions, including east, north, northeast, and northwest trends. When several sets intersect, they can divide rock into shapes that appear rectangular, angular, or polygonal. A joint is a fracture along which there has been little obvious movement. It is not quite the same as a fault, where rock on one side has shifted relative to the other, though the distinction can become difficult after long weathering. Joints often form in sets because the forces acting on a large rock mass are not random at every point. If stress affects a broad area in a consistent direction, many cracks may develop with similar orientations. Another set can later cross the first, add a third set, and the rock may be divided into blocks with repeated angles. The result is not as regular as a brick wall, but it can be regular enough to suggest planning, especially after erosion removes smaller fragments and leaves the largest masses exposed. Granite is particularly good at producing this effect. It is strong, but it contains mineral grains that expand, contract, and weather at different rates. Water enters the joints and begins altering exposed minerals. Feldspars can break down into clay minerals, weakening the rock along the edges. In cold climates, water freezes within cracks and expands, then melts and allows more water to enter. This does not normally split an enormous block in one dramatic event. The process works through repetition. A narrow weakness becomes wider, grains loosen, small fragments fall out. Roots find the opening and add pressure. A block that began as part of a continuous outcrop becomes increasingly isolated from the mass around it. The finished appearance can resemble construction, because the major fractures established the broad shape before weathering cleaned and widened the boundaries. The phrase "finished appearance" can be misleading, because nothing about the process is truly finished. The wall is still changing. Freezing, thawing, moisture, tree growth, gravity, and surface erosion continue to act on it. The owners themselves suggest that the lower southeastern edge may once have stood higher, and that portions could have broken apart through earthquakes, freeze-thaw action, and tree roots. That interpretation is not proof of either construction or natural formation, but it reminds us that the present outline is only the current stage of a much longer sequence. A section that now looks like rubble at the foot of a wall may be material that detached naturally from an outcrop. It could also resemble the collapse of built masonry. The visible result alone cannot tell us which sequence occurred. The apparent horizontal alignment is perhaps more persuasive than any individual block. People expect natural cliffs to be irregular. When several large masses appear to follow one level line, the arrangement resembles a course laid by builders. At Sage Wall, parts of the exposed face seem to maintain a common direction over a substantial distance. From some viewing positions, the upper edge also appears unusually straight. This has encouraged descriptions of the formation as a planned boundary, retaining wall, platform edge, or surviving part of a larger complex. The longer the line appears, the less likely coincidence feels. Yet straightness is difficult to judge without a proper survey. A line can look straight when viewed from one location because irregularities overlap in perspective. A curved or stepped face may appear aligned when photographed from the front. Vegetation can hide recesses. Fallen blocks can fill low sections. Light can connect separate shadows into one continuous seam. Even the choice of where the wall begins and ends affects the measurement. If an observer selects only the most regular section, the result will look more artificial than the entire exposure. A reliable assessment would require coordinates taken along the face, measurements of elevation, and a three-dimensional model showing how much the surface actually deviates from a plane. The word alignment also needs a reference. Aligned with what? The formation may follow a major joint direction within the granite. It may follow the local slope or the edge of a resistant rock mass. It may face a valley because erosion removed material more effectively on that side. A structure built by people could follow the same natural features, since builders often use the easiest available foundation. The alignment becomes stronger evidence of design only when it is shown to serve a consistent purpose that natural processes do not explain well. Imagine drawing a line through the most prominent faces of the wall. If that line is compared only with the nearby trees, it may appear remarkably precise. If it is compared with mapped joint sets across the batholith, it may turn out to follow a common fracture orientation. That would not make the formation uninteresting. It would connect its geometry to the stresses that affected the surrounding rock. If the alignment instead cuts across the known geological structure, remains unusually planar through changing terrain, and includes blocks that can be shown to have been moved, the construction claim would become more difficult to dismiss. The important step is comparison. A number has little meaning until we know what range natural formations in the same setting commonly produce. Angles create the same problem. A right angle looks designed because right angles are central to buildings, furniture, roads, screens, books, and almost everything else people attempt to fit into a room. But right angles also occur when two fracture sets intersect at approximately 90 degrees. The angle need not be perfect. Weathering can sharpen one portion and round another, leaving a corner that appears carefully cut from a distance. Three intersecting planes can create something close to a rectangular block. If one plane is tilted, the result becomes a five-sided or six-sided form that resembles polygonal masonry. Supporters of the artificial interpretation sometimes argue that natural cracks should continue through several supposed blocks, while masonry joints should stop and change direction at their edges. This can be a useful observation, but it must be documented carefully. A crack may appear to stop because it narrows, turns away from the surface, becomes hidden by soil, or merges with another fracture. On the other hand, repeated seams that consistently terminate at fitted boundaries could support the idea of separate place stones. High-resolution mapping would allow researchers to trace these lines rather than relying on selected photographs. A complete fracture map could show whether the pattern behaves like a jointed rock mass or a constructed wall. One sign that would strongly favour natural formation is continuity behind the visible face. Suppose a supposed block appears rectangular at the front but remains attached to a larger granite body several feet behind it. In that case, it was not carried into position as a finished stone. It could still have been shaped on the exposed side, but the claim would change from construction to modification. Conversely, if several massive blocks are fully separate, rest on prepared material, and consist of stone traced to a different source, the argument for deliberate placement would become much stronger. At present, the publicly available material does not provide that level of demonstration. The size of the stones adds emotional weight to the question, but does not identify their origin. A very large block seems harder to explain as human work, because moving it would require organisation and engineering. At the same time, its size makes a natural origin entirely ordinary within a batholith. The parent rock body is vastly larger than any visible block. Natural fractures do not have to lift the stone, transport it across a valley, and place it in a row. They only have to divide rock that is already present. Gravity may shift a section a few centimetres, or tilt it after support erodes away. That small movement can create the appearance of a separate stone fitted against its neighbour. A construction theory must therefore explain more than how ancient people could move large objects. It must show that movement occurred. This might be demonstrated by a block sitting across the local bedding or joint pattern, by a foreign stone type placed among the granite, by packing stones beneath it, or by wear and modification consistent with transport. Without those signs, great size does not favour construction. It simply makes the visual resemblance more impressive. There is also a tendency to treat irregularity as evidence of sophisticated building. When the blocks are not rectangular, supporters may describe them as polygonal and therefore more advanced. When surfaces do not meet neatly, the gaps may be explained as damage. When the upper line is uneven, missing courses may be blamed. A theory that can absorb every observation becomes difficult to test. The same danger exists on the geological side. If every straight face is called a joint, every gap is called weathering, and every odd mark is declared natural without examination, that explanation also becomes too flexible. Each interpretation should risk being wrong. It should identify the observations that would contradict it. For a natural jointing model, researchers could predict that the apparent blocks will remain connected to bedrock, that seam directions will match regional fracture sets, and that similar forms will appear in nearby untouched exposures. The mineral composition should be consistent with the surrounding intrusion, and weathering should be concentrated along joints and grain boundaries. For a construction model, researchers could predict that at least some stones were detached, moved, shaped, supported, or arranged in ways that cut across the natural structure. Repeated tool traces or prepared contact surfaces might be present. Material beneath the blocks could contain evidence of deliberate foundation work. The formation might also have a clear architectural plan extending beyond the most wall-like section. The idea of an architectural plan is important because individual stones can be deceptive. Human structures usually organise space. A wall may define an enclosure, support a terrace, protect an entrance, hold back soil, or form part of a larger building. If Sage Wall belongs to a megalithic complex, investigators should be able to identify related features that make sense together. There should be corners, returns, parallel lines, passages, platforms or foundations arranged according to some practical design. Randomly selecting every nearby ridge and boulder as part of the same complex would not be enough. The proposed plan must be clearer than the natural topography, and should make predictions about where additional features will be found. Some visitors believe they can see such a larger arrangement. They point to stones beyond the main face, possible collapsed sections and shapes partly hidden by soil and vegetation. These observations deserve mapping, but mapping must come before naming. A pile of granite beside the wall could be collapsed masonry, frost-shattered bedrock, slope debris, or a combination of processes. Calling it a tower or platform creates a mental picture that may influence every later observation. A neutral survey would record dimensions, positions, elevations, and materials first, then compare possible explanations. Lighting can have an unexpectedly large effect on all of this. Low sunlight entering from the side deepens seams and emphasizes relief. Midday light flattens the same surface. Snow can outline gaps and make blocks appear sharply separated. Wet granite darkens, while fractures containing soil or vegetation may become darker still. A video filmed while walking produces changing perspective, causing edges to align for a moment and then separate. This does not mean photographs are useless. It means that dramatic images should be supported by measurements that remain the same when the light changes. The human eye also tends to complete missing lines. If two horizontal seams appear on either side of an obstruction, the mind connects them behind it. If a tree hides part of the rock, we imagine the simplest continuation. That continuation may be correct, but it may also create a longer alignment than the actual surface contains. Three-dimensional scans can reduce this problem by recording the entire visible face and allowing measurements from many viewpoints. The Sage Mountain Center reports interest in LIDAR and other non-invasive surveys, but the public evidence has not yet produced a widely accepted demonstration that the visible blocks form constructed courses. Even the term wall influences perception. If the formation had first become known as the Sage Granite Outcrop, visitors might approach it differently. A name does not change the stone, but it provides an instruction for looking. Once we are told that an object is a wall, we search for blocks, joints, collapse, entrances, and purpose. A geologist hearing the word outcrop searches for mineral texture, joint orientation, weathering, and connection to bedrock. Neither set of questions is wrong, but the starting label changes what feels important. This does not mean the mystery is only psychological. There is a real formation, and it has real measurable properties. The challenge is to prevent the visual power of the site from moving ahead of the evidence. A straight-looking line can be measured, an angle can be recorded, a seam can be followed. A block can be tested to see whether it is detached. The wall's geometry can be compared with nearby granite exposures and regional structural maps. None of these tasks requires anyone to abandon curiosity. They simply turn curiosity into a method. Suppose a complete survey showed that the main face follows one dominant joint set, while the divisions between apparent blocks follow two crossing sets. Suppose similar patterns occurred nearby, though on a smaller scale. That result would strongly support a natural origin. The wall could still be unusually large and visually striking, but its order would emerge from regional geology. Now suppose the survey instead showed repeated blocks placed with their natural fracture directions rotated, supported on smaller stones, and arranged into courses that remain level despite changes in the bedrock. That would move the discussion toward construction. The value of these hypothetical results is that they show what useful evidence looks like. It does not merely add another impressive detail, it distinguishes between explanations. Until such evidence is available in a form that specialists can examine independently, the phrase impossible alignment should be handled gently. The alignment may be unusual, it may deserve study, it may even prove important. Calling it impossible assumes that natural jointing, erosion, perspective, and selection have already been ruled out, and they have not. Nature does not need to create a perfect wall to create the appearance of one. It only needs to expose a long fracture-controlled face, divide it with intersecting joints, and allow weathering to emphasize the boundaries. Standing close to Sage Wall, however, explanations about joint sets may feel less satisfying than they do on paper. The stones are large, the seams are visible, and certain contacts seem almost too neat. You can place a hand against the granite and follow a line that disappears beneath another mass. Some corners appear to have been adjusted. Some surfaces seem flatter than the neighbouring rock. It is easy to understand why a visitor might leave, believing that geology alone cannot account for what they saw. That reaction is worth respecting without treating it as a conclusion. Direct experience can reveal details that photographs miss, but it can also strengthen the effects of scale, expectation, and selective attention. The best response is not to tell visitors that they saw nothing unusual. It is to ask which exact feature seems least compatible with natural formation, record it, and test it. If the answer is the long alignment, survey the alignment. If it is the fitted angles, map every angle rather than the most impressive examples. If it is the separation between blocks, determine whether those blocks are truly separate. Once the large geometry has been examined, attention naturally shifts to smaller details on the stone. Several protrusions have been described as knobs resembling features found on worked megalithic blocks elsewhere. Shallow depressions and cup-shaped marks have also been interpreted as possible evidence of tools, lifting methods, ritual activity, or an unknown construction process. These features are easier to overlook than the wall's main alignment, but they may be more useful if their shape, distribution, and origin can be established, because a mountain can produce a straight fracture, while a repeated pattern of deliberate modification would require a different explanation. Once attention moves away from the overall alignment of Sage Wall and settles on the stone itself, the argument becomes more detailed. The wall-like face may be the feature that first catches the eye, but the smaller forms on its surface are often presented as the more persuasive clues. Visitors have reported rounded protrusions that look like knobs, shallow circular depressions that resemble cups, narrow grooves, rough patches beside smoother surfaces, and changes in colour or texture from one block-like mass to another. None of these features is as dramatic as a 24-foot wall made from enormous pieces of granite. Yet small details can matter more than scale. A mountain can produce a large fracture without anyone touching it. A repeated mark made in the same way across several surfaces would be harder to explain as coincidence. This is why supporters of the megalithic interpretation spend so much time looking closely at the rock, sometimes closely enough that an ordinary walk becomes a long inspection of every bump, hollow, and suspiciously organised patch of lichen. The protrusions are usually described as knobs, nubs, or bosses. They are rounded or irregular masses of stone that project from an otherwise flatter surface. Similar-looking features occur on confirmed ancient masonry in several parts of the world, particularly on large stone blocks where a raised section was deliberately left standing proud of the finished face. Archaeologists and stoneworkers have proposed several practical reasons for such projections at known constructed sites. A boss may have helped workers handle a block, attach ropes, control its position, or leave extra material for later finishing. In other cases, it may have served a decorative or symbolic purpose, or it may simply show that the stone face was never fully dressed. The important phrase is at known constructed sites, because a feature can be interpreted as a lifting boss only after the stone around it has been shown to be worked masonry. A bump on natural granite does not become an ancient lifting device merely because it resembles one in Peru, Egypt, India, or anywhere else with very photogenic stones. At Sage Wall, photographs and visitor reports have drawn attention to protrusions of different sizes on several sections of the formation. A widely circulated argument claims that these knobs strengthen the comparison with polygonal megalithic walls elsewhere. Some independent promoters of the artificial interpretation describe the similarity as a repeated global construction signature. The official Sage Mountain Centre material, however, does not publish a specialist archaeological analysis demonstrating that the protrusions were carved, positioned according to a pattern, or used during construction. The site presents ongoing research and a range of possible interpretations, but its publicly available reports do not establish the knobs as human-made features. That distinction is easy to lose when a video moves quickly from a close-up in Montana to a close-up at a confirmed archaeological site, and allows visual similarity to do the rest of the argument. The two objects may look alike, but appearance alone does not show that they formed through the same process. Natural granite can produce projections for several reasons. The rock may appear uniform from a distance while containing minerals, veins, and small zones that resist weathering differently. Quartz-rich portions can remain raised as nearby feldspar and mica break down. A hard mineral vein may cross a softer surface and stand out after the surrounding material has eroded. A fractured edge may round while its centre remains intact, leaving a bulge. Thin sheets can detach from parts of a face while protected areas survive. Lichen may shield one patch more effectively than another, and water may repeatedly follow the same route around it. None of these processes requires the rock to be soft in the ordinary sense. Weathering works grain by grain, season after season, and has no concern for the impatience of visitors who would prefer a result before lunch. Differential weathering is especially important because it explains how neighbouring parts of the same granite surface can develop very different shapes. Granite contains several minerals with different chemical and physical properties. Feldspars can alter through reactions with water, producing clay minerals and weakening the surface. Biotite can break down and release iron, contributing to stains and local changes. Quartz is often more resistant. Moisture enters microscopic openings, freezing and thawing adds stress, and loose grains are removed by wind, runoff or gravity. A harder patch is left standing while the area around it lowers. Given enough time, the surviving patch can resemble a deliberately retained boss. Research on cavernous weathering also shows that resistant walls, ridges, tendrils, and isolated knobs can remain after adjacent pits enlarge and merge. Such forms are not limited to sandstone. Tuffone and related weathering cavities occur in granite as well. This does not prove that every protrusion at Sage Wall is natural. It shows why shape alone is insufficient. A proper examination would ask whether the knobs are made from the same uninterrupted granite as the surface behind them, whether their mineral composition differs from the surrounding stone, whether fractures outline them, and whether microscopic marks indicate pecking, grinding, or impact. Deliberately worked stone often records the actions used to shape it. Repeated blows can leave crushed grains, overlapping pits, directional scars, or a surface texture that differs from weathered granite. Grinding may smooth high points and create patterned abrasion. Natural weathering can soften or erase these traces, especially over a long period, but a convincing claim would need more than a rounded form seen in favourable light. Distribution would matter as well. If the protrusions occur randomly on exposed surfaces, including nearby natural boulders, a geological explanation becomes stronger. If they appear at consistent positions on supposed blocks, perhaps near lower corners or centres of faces, and if their dimensions follow a repeated range, deliberate design becomes more plausible. The same principle applies to almost any disputed mark. One example invites a story. A statistically meaningful pattern begins to test the story. Researchers would need a full inventory rather than a collection of the best photographs. Every protrusion should be measured, mapped and compared with the surrounding terrain. The less impressive examples matter because they reveal whether the apparent pattern survives when selection is removed. The cup-shaped depressions create a related but slightly different problem. Genuine archaeological cupules are human-made hollows that were commonly pecked or ground into rock surfaces. They occur in many parts of the world and can appear alone, in groups, or with rings and grooves. At documented prehistoric rock art sites, their cultural meanings are often uncertain even when their artificial origin is accepted. Some may have been symbolic, ceremonial, practical, or connected with repeated actions that are no longer understood. Historic England describes cup and ring markings as small cup-like hollows pecked into natural rock, sometimes surrounded by one or more rings and linked by grooves. Research on cupules emphasises that they may look simple, while requiring substantial repeated impact to create, especially in hard stone. Their interpretation depends on morphology, production traces, context and association with other archaeological evidence. The word cupule, should therefore not be used as a general name for every rounded hollow, and carries an implication of human production. A neutral description such as pit, depression, hollow or basin is safer until the origin has been examined. Even archaeologists working at established rock art regions sometimes find it difficult to distinguish pecked cupules from natural concavities or small functional grinding features. The San Diego Archaeological Center notes that this distinction can be problematic in some cases, particularly when the marks are isolated or weathered. If specialists face that difficulty at sites where human activity is already well documented, a few hollows on a disputed granite formation in Montana cannot settle the question by themselves. Natural pits can begin at tiny weaknesses in the stone. A mineral grain may weather faster than its neighbours. Water may collect in a shallow irregularity and keep the surface damp longer than the surrounding rock. Chemical alteration loosens grains, which are then removed, making the hollow slightly deeper. The deeper hollow retains more moisture and creates a sheltered microenvironment, accelerating the same process. This feedback can turn a minor surface difference into a rounded cavity. In other settings, salts crystallize between mineral grains and force them apart. The National Park Service describes Tafoni as rounded, smooth-edged openings created through focused weathering, and it documents dramatic examples on granite boulders at City of Rocks National Reserve. The exact processes vary with climate, minerals, moisture, exposure, and the structure of the rock, but the useful lesson is simple. Naturally formed holes can be surprisingly regular. Small basins can also form on upper surfaces where water remains after rain or snowmelt. Repeated wetting encourages chemical weathering, while ice can loosen grains during cold periods. Leaves, needles, soil, and organic acids may collect in the depression. Windblown grit can add abrasion. The hollow gradually expands, sometimes developing a smoother interior than the surrounding surface. If the basin later becomes tilted by movement of a block or exposed on a different face, its original relationship with drainage may no longer be obvious. A visitor can then see a cup on a near vertical surface and reasonably wonder why water would have formed it there, even though the rock's orientation or exposure history may have changed. To argue that the Sage Wall depressions were deliberately made, investigators would want to see repeated impact traces, comparable diameters and depths, patterned placement, or association with clear grooves and worked surfaces. Fresh experiments can help by showing how pecking granite with stone tools changes the grain structure. Three-dimensional scanning can record the cross-section of each hollow. A deliberately pecked cup may have a different profile from a cavity formed by grains loosening along mineral boundaries, although long weathering can blur the distinction. Microscopic examination may reveal whether the surface was battered, abraded, dissolved, flaked, or broken naturally. None of this needs to damage the wall significantly. Portable imaging, close-range photogrammetry, and carefully chosen microscopic samples can answer more than another round of pointing at a photograph. Context is even more important than shape. Confirmed cup-marked sites often occur within wider archaeological landscapes containing burials, structures, tools, settlements, or other rock art. The marks may form groups or repeated designs. At Sage Wall, no accepted archaeological context currently connects the reported depressions to a known prehistoric activity. No published artifact assemblage has been presented beside them, and there is no established dating sequence showing when they appeared. This absence does not prove that people never made or used the marks, but it prevents the depressions from carrying the same evidential weight as cupules documented within a secure cultural setting. A cup-like shape without context is a question, not an artifact. There is another complication. Human marks and natural marks can occur on the same surface. People have always interacted with unusual rocks. A natural hollow might be deepened, widened, or reused. A projecting knob might be struck, rubbed, or incorporated into a later activity. A visitor from centuries or thousands of years ago did not need to believe that Sage Wall was an artificial monument in order to find the formation useful or significant. The rock could have served as a landmark, shelter, meeting place, hunting reference, spiritual location, or simply a convenient place to sit while someone else explained directions rather badly. If future research finds a few modified hollows, that would demonstrate human interaction, but it would not automatically prove that the entire 275-foot formation was constructed. This distinction between modification and construction is essential. Imagine finding a carved symbol on a natural cliff. The symbol is human-made, but the cliff is not. A staircase cut into bedrock is artificial in one sense, though the rock mass itself formed naturally. A retaining wall built against a natural outcrop may combine placed stone with untouched granite. Sage wall could contain several histories at once. The main body might be geological, with later people modifying selected features. Alternatively, the apparent marks may all be natural. The evidence should be allowed to support a mixed explanation rather than being forced into a choice between a lost metropolis and an untouched mountain. Claims about grooves deserve the same care. Straight or curved channels on stone can be created by tools, repeated rubbing, water flow, mineral veins, roots, or fractures that have weathered open. A groove that links several cup-shaped depressions may resemble known rock art designs, but its surface texture and path need to be studied. Water tends to follow gravity, although the block may not remain in its original position. A mineral vein can cross the rock independently of present slope. A human groove may show consistent width, repeated pecking, or an intentional relationship with other marks. Calling a line a channel, cut, or inscription before those details are known changes the question too early. The colour differences at Sage Wall have also attracted attention. The official site reports that samples from the upper and lower portions were analysed because the top horizontal course looked darker and had a slightly different texture. According to the owner's summary, the samples appeared mineralogically similar, while the darker appearance was interpreted as weathering and greater exposure. They also noted that nearby boulders at a similar elevation did not show exactly the same discoloration or texture, leaving them with further questions. This is a useful example of a real observation that does not yet require an extraordinary explanation. Surface colour can vary because of moisture, oxidation, lichen, runoff, sun exposure, roughness, biological films, and the orientation of the face. If the underlying mineralogy is similar, the difference may record environmental history rather than separate building material. Surface texture can be equally deceptive. A face that appears smooth may have formed along a natural joint, where the rock split through a relatively flat plane. A rougher face may be an exterior weathering surface exposed for much longer. If one block-like section broke away recently in geological terms, the revealed surface could look cleaner and more finished than the older surface beside it. Conversely, deliberate dressing could also make one face smoother. To distinguish the possibilities, researchers would examine weathering rind thickness, lichen cover, microfractures, and the way mineral grains intersect the surface. A natural joint plane may cut through crystals, while a worked surface may crush or truncate them differently. The answer is likely to be written at a scale too small for the unaided eye. Knobs and cups become most persuasive when they are discussed through analogy. A presenter shows a raised boss at a famous ancient wall, then a protrusion at Sage Wall. Next comes a cup mark from a recognised archaeological site, followed by a hollow in Montana. The viewer is invited to conclude that the same builders, the same technique, or the same lost knowledge connects them. The argument feels efficient because the images appear to explain one another, yet analogy can only identify a possibility. It does not date a feature, show cultural contact, or demonstrate a shared manufacturing method. Similar practical problems can produce similar human solutions, and similar physical processes can produce similar natural shapes. A round hollow is one of the simplest forms available to either a person striking stone or water weathering it. A more reliable comparison would include measurements and control samples. How many knobs occur per square metre at Sage Wall? How many occur on nearby granite exposures? Are they concentrated on particular orientations? Do their bases show cutting or natural mineral continuity? How deep are the depressions, and what are their diameter to depth ratios? Are the interiors smoother than natural pits nearby? Do any preserve percussion scars? Are grooves connected to them in repeated arrangements? These questions are not as exciting as announcing that every ancient culture left the same mysterious signature, but they can turn resemblance into evidence. The surrounding environment offers a ready-made control group. The boulder batholith contains extensive weathered granite, including rounded boulders and fractured exposures. Researchers do not need to compare Sage Wall only with monuments on other continents. They can compare it first with stone formed from the same intrusive system under similar climate and elevation. If knobs, pits, grooves, and flat joint surfaces occur commonly nearby, the unusual details become part of a local weathering pattern. If Sage Wall contains a concentration or arrangement not found anywhere else in comparable rock, the case for further archaeological investigation grows stronger. Local comparison is less glamorous than matching Montana with Machu Picchu, but it is far more diagnostic. There is also a preservation issue. The formation is on private land and has received growing visitor attention. Touching, climbing, scraping, taking samples, or attempting to clean the stone could destroy the very evidence people hope to study. A faint impact trace can be damaged by a modern boot or metal tool. Lichen removal can alter surfaces and erase biological information. Even chalking a groove to make it visible in a photograph can contaminate it. The Sage Mountain Center states that its research strategy has emphasized non-invasive methods before considering excavation, which is sensible for a site whose significance remains disputed. Detailed recording should come before physical intervention, and sampling should be designed by specialists who know what information may be lost. For now, the knobs and cup-shaped marks do not provide decisive proof of prehistoric construction. They are genuine visible features, at least in the ordinary sense that protrusions and depressions can be photographed and examined. Their interpretation remains open. Natural differential weathering provides credible mechanisms for creating resistant knobs, pits, hollows, grooves, and contrasting textures in granite. Archaeology also provides examples of people deliberately producing bosses and cupules on stone. The task is not to decide which category looks more exciting. It is to identify the microscopic traces, spatial patterns, and surrounding context that separate one origin from the other. The smaller details therefore leave us in an interesting position. They do not settle the artificiality of Sage Wall, but they show exactly where future work could become useful. If the marks are mapped comprehensively and compared with nearby outcrops, much of the uncertainty may narrow. If repeated tool traces appear, the discussion will change immediately. If mineral continuity and weathering patterns explain them, the geological case will become stronger. Until then, each knob remains a raised patch of granite carrying several possible stories, and each cup remains a hollow that asks for examination rather than a label. Attention then moves from the stone surface to the ground beneath it. The visible wall seems to disappear into soil and broken granite, encouraging the idea that the exposed blocks are only the upper part of something much deeper. Reports of geophysical reflectors, probing that did not strike rock at shallow depth, and possible buried continuation have become central to the claim that Sage Wall rests on a foundation or extends underground. Those claims require a different kind of evidence, because once the eye can no longer follow the stone directly, instruments must interpret what lies below. The ground at the foot of Sage Wall looks ordinary enough at first. There is soil, decomposed granite, fallen needles, roots, loose stone, and the uneven surface expected on a forested Montana mountainside. The lowest visible blocks disappear into this material rather than ending neatly on an exposed platform. That simple fact has become one of the most important parts of the mystery. If the formation is natural, the granite may continue below the surface as bedrock or as partially separated masses surrounded by material produced through weathering. If it was constructed, the visible blocks may rest on a prepared foundation, and additional courses may remain buried beneath centuries of soil and debris. Both explanations begin with the same observation. Only part of the stone can currently be seen. The difficulty lies in discovering what continues below without removing enough ground to damage a site that may be archaeologically important, geologically unusual, or both. Supporters of the prehistoric construction theory often describe the visible face as the upper portion of a much larger structure. In this interpretation, the wall did not begin at the present ground level. The soil accumulated after construction, covering lower courses and perhaps concealing a wide base designed to support the enormous blocks above. The partially buried continuation at one end is sometimes treated as evidence that the exposed section is only a surviving fragment. If the structure extends downward by 10 feet or more, its total scale would be considerably greater than the familiar photographs suggest. A wall already reported as roughly 275 feet long and up to 24 feet high would become a major engineering project, requiring not only the movement or shaping of granite, but also the preparation of stable ground beneath it. The builders would have needed to understand how the mountainside carried weight, how water moved through the soil, and how to prevent the lowest stones from sliding or settling. This is an impressive possibility, although the underground measurements published so far do not demonstrate that such builders existed. The Sage Mountain Center reports that ground-penetrating radar work has identified what the owners describe in their personal takeaways as a reflector or possible base beneath the wall. They also state that portions may continue more than 10 feet below the present surface. At the eastern base, they say a physical probe was pushed down 4 feet, the limit of the probe, without striking rock. They intend to continue the investigation. These are useful observations, but the wording matters. This site presents them as personal interpretations gleaned from a geophysical report, not as the conclusion of an archaeological excavation establishing a constructed foundation. The term reflector describes a response in radar data. It does not identify the object or material that produced the response, and it certainly does not arrive with a label explaining whether it was placed by ancient workers or formed within the mountain. Ground-penetrating radar works by transmitting short pulses of electromagnetic energy into the subsurface. When that energy reaches an interface between materials with sufficiently different electromagnetic properties, part of it may return to the receiver. The recorded travel time and signal strength can help estimate the depth and geometry of the reflecting boundary. A radar profile can reveal layers, changes in moisture, bedrock surfaces, voids, buried objects, disturbed soil, and other features that contrast with the material around them. What it does not do is photograph the underground in the familiar sense. The shapes visible in a radargram are processed representations of reflected energy, and several different physical conditions can produce similar-looking signals. Imagine tapping a wall in a dark room and listening for changes in the sound. A hollow space might sound different from solid material, but so might a change in thickness or composition. GPR is far more sophisticated than tapping plaster with a knuckle, but the broad problem is similar. The instrument detects contrasts. Interpretation must determine what created them. At Sage Wall, a strong reflector below the visible granite might represent the contact between decomposed granite and solid bedrock. It could mark a fracture plane, a moisture boundary, a layer of loose blocks, a buried stone surface, or a prepared architectural base. The data may narrow the possibilities by showing shape and continuity, but the presence of a reflection alone cannot choose among them. Moisture is particularly important because water has a strong effect on the electrical properties measured by radar. A layer of damp soil can contrast sharply with dry decomposed granite. Water may collect above a less permeable rock surface, or within fractures at the base of the outcrop. Roots and organic material can alter moisture locally, while seasonal snowmelt may produce conditions very different from those found later in summer. The same survey line could therefore respond differently, depending on when the measurements were taken. Reliable interpretation requires attention to soil conditions, weather, antenna frequency, survey spacing, local topography, and the estimated velocity of the radar signal through the ground. Depth is calculated from travel time and assumed or measured signal velocity, so an inaccurate velocity estimate can make a reflector appear shallower or deeper than it actually is. There is also a trade-off between depth and detail. Higher frequency antennas can reveal smaller features but usually do not penetrate as deeply. Lower frequencies can reach farther while producing a less detailed image. Conductive materials, including some wet or clay-rich soils, can weaken the signal rapidly. Dry, sandy, well-drained ground is generally more favourable. The soil around Sage Wall is described by the property owners as having an upper organic layer above decomposed granite, a porous, sandy material created as granite deteriorates. Such conditions may permit useful radar penetration in some places, but boulders, roots, variable moisture and steep topography can still create complicated reflections. The topography is not a small inconvenience. Most people imagine a radar instrument moving over a level field while the subsurface layers lie neatly beneath it. Sage Wall sits on a slope beside large exposed stone. Radar waves spread through the ground rather than travelling only in a perfectly vertical line. A signal recorded at one surface position may have reflected from an object offset to the side. Sloping surfaces and dipping fractures can appear distorted until processing accounts for their geometry. Nearby exposed blocks may also contribute unwanted signals. The EPA notes that surface objects and other sources can create artificial reflectors in a subsurface record, while point-like objects can appear as hyperbolas rather than as their true shapes. Processing methods can help focus these responses, but the final image remains an interpretation built from physical measurements and assumptions. This is why the word base should not be treated as interchangeable with foundation. Every large outcrop has a base in the ordinary sense that the visible rock continues, ends, or meets another material below ground. A constructed foundation is a much more specific feature. It is deliberately prepared to distribute weight and stabilize a structure. It may consist of large footing stones, compacted fill, a cut bedrock shelf, gravel, smaller packing stones, or some combination of these. To identify such a foundation, researchers would look for geometry and material relationships that natural processes do not readily explain. A level surface extending at a consistent angle beneath separately placed stones would be interesting. A trench cut into undisturbed soil and filled with selected material would be stronger. Tool marks, packing stones, disturbed layers, and cultural material would strengthen the case further. A radar reflector can help locate a place to investigate, but it cannot by itself show that the surface was prepared. The claim that a probe descended 4 feet without striking rock is similarly suggestive, but limited. A narrow probe tests only one small path through the ground. Missing solid stone at that point could mean the visible block does not continue directly downward. It could also mean the probe passed through loose, decomposed granite beside a natural rock face, entered a wide fracture, followed a gap between boulders, or moved through accumulated slope material. If the probe had struck rock immediately, that would not have proved the wall natural, because a built block or footing could also lie below. If it did not strike rock, that does not prove the block was placed on an artificial support. The observation becomes valuable when repeated along carefully recorded lines and compared with geophysical data. A grid of tests can reveal a pattern. One hole mainly reveals what happened in one hole. A natural granite outcrop can extend deeply without preserving the same wall-like face below the ground. The exposed portion is shaped by weathering at the surface, while buried stone experiences different moisture, temperature, and chemical conditions. A sharp face may gradually become irregular underground. Joints visible above may narrow, widen, or turn. Large blocks may be surrounded by decomposed granite formed as feldspar and other minerals break down. The transition from solid rock to loose granular material can be abrupt in one location, and gradual in another. If radar detects a broad boundary below the formation, that could record the base of a weathered zone rather than a floor constructed beneath a wall. One common form of granite weathering begins along joints beneath the ground. Water reaches the corners and edges of blocks from more than one direction, causing those areas to alter faster than the protected interior. Over time, the material around the surviving core becomes loose and can later be removed by erosion, exposing rounded boulders. In a strongly jointed mass, some parts remain as large angular blocks while others decompose into sandy grus. A buried contact between fresher granite and weathered material could appear regular over a short distance because it follows a joint or fracture surface. Once exposed, it might be mistaken for the bottom of a placed stone. The construction interpretation faces a different set of practical questions. If the visible blocks continue more than 10 feet downward, are they single upright masses, or are there additional horizontal courses? A single natural slab partly buried in the slope would produce one kind of radar pattern. A stack of separate blocks would produce several contacts, although closely fitted granite with little contrast between pieces might be difficult for the instrument to distinguish. If a broad horizontal surface extends outward from the wall, is it a footing, natural bedrock, or a fracture plane? If supposed blocks sit in individual sockets or cradles, do those depressions show cutting, or could they be natural weathering around harder rock? Geophysics can suggest where these relationships occur, but direct observation is usually needed to identify their origin. There are archaeological sites where GPR has successfully detected buried walls and foundations. In those cases, the interpretation is strongest when the anomalies have a repeated architectural plan, when they contrast clearly with the surrounding soil, and when excavation or known structures provide calibration. Closely spaced survey lines can be processed into time slices, showing how anomalies change with depth. A straight response that forms corners, rooms, corridors, or parallel foundations is easier to recognize as architecture than a single reflector beneath one large rock exposure. Historic England's guidance emphasizes that geophysical techniques measure different physical properties and that the appropriate method depends on the site, its geology, and the question being asked. Experienced interpretation is essential because no single technique works best under every condition. At Sage Wall, the most useful next step would not be to ask radar alone for a final answer. It would be to combine several methods. Additional GPR lines collected as a dense grid could show whether the reflector remains continuous in 3 dimensions. Electrical resistivity tomography could examine differences between solid granite, weathered material, moisture-rich zones, possible voids, and loose fill. Seismic methods could estimate changes in rock competence and fracture density. Magnetic and electromagnetic surveys could map mineral variations, although those readings would need to be separated from claims about human technology. Detailed topographic data could place every underground anomaly in relation to the visible blocks and the mountain slope. Geophysical methods are often most effective when their results are compared rather than interpreted independently. Studies at confirmed archaeological sites have shown that combining GPR and resistivity can improve the identification of buried walls because each responds to different material properties. Even then, a targeted excavation might eventually be required. This does not mean removing the wall or digging an enormous trench along its entire length. A carefully selected narrow excavation could expose one critical contact while preserving the wider site. Researchers might choose a place where the radar suggests a horizontal reflector crossing beneath a clearly defined block. Soil would be removed by recorded layers rather than shoveled away as general debris. Each change in colour, texture and composition would be documented. Samples could be taken for sediment analysis. Any charcoal, organic matter or artifacts would be recorded in their exact positions. The contact beneath the granite could then be examined directly. If the block rests on undisturbed weathered bedrock, the natural explanation would gain support. If it sits on deliberately compacted material, smaller packing stones, or a cut platform, the interpretation would change. If the lower part remains attached to a continuous granite body, the idea that it was transported into place would become very difficult to maintain. If it is fully separate and positioned across the natural fracture pattern, construction would become more plausible. The goal would not be to find a spectacular object. It would be to observe a relationship that distinguishes between competing histories. Excavation could also search for evidence of soil disturbance. Digging a foundation trench mixes layers that originally formed at different times. A prehistoric construction project involving blocks of this scale should have displaced a great deal of material. Even if erosion removed much of it, remnants might survive in protected areas. Researchers could look for fill containing angular chips from stone shaping, material transported from elsewhere, or a sequence inconsistent with natural slope formation. Archaeological excavation is useful not because every trench reveals tools or bones, but because the order of deposits records events. A foundation cut interrupts older layers and is later filled. Natural soil development tends to produce a different sequence. Dating would remain difficult. Granite cannot be radiocarbon dated, and its geological age tells us when the magma crystallized rather than when a block might have been moved. Finding ancient granite in an ancient granite batholith is not a particularly dramatic surprise. Researchers would need datable material associated securely with any construction event. Charcoal beneath a placed block could provide a minimum or approximate construction date if it genuinely belonged to the foundation and had not moved through roots or animal burrows. Luminescence methods might estimate when certain sediments were last exposed to light, although suitability would depend on the deposits. Lichen and surface weathering estimates are generally less direct and require local calibration. A date without secure context could mislead just as easily as an undated block. The absence of artifacts remains an important issue. A structure of the proposed scale would imply planning, labour, repeated activity, and probably a nearby human presence. Construction workers need tools, food, temporary shelter, and routes into the site. Yet no publicly established archaeological assemblage has been presented from Sage Wall. This does not make human construction impossible. Mountain sites can lose evidence through erosion, acidic soils, later disturbance, and limited investigation. People may have visited seasonally rather than living there permanently. Stone and wooden tools could be difficult to recognise after long weathering. Still, the artifact problem cannot be solved simply by saying that everything disappeared. A theory must explain what evidence should remain and then test for it. The alleged continuation beyond the main visible section presents another underground question. The owners interpret LIDAR imagery as suggesting that Sage Wall may continue partially buried for at least another 100 feet. They also see possible parallel walls or channels elsewhere on the mountainside, but they state that a specialist analysis of the LIDAR data has not yet been completed and identify these observations as personal takeaways. LIDAR records surface elevation, including subtle changes beneath vegetation after the data are processed. It can reveal ridges, terraces, depressions, and alignments, but it cannot see deeply through soil or determine whether a buried ridge is made from placed masonry. A natural bedrock spine following a fracture could create the same surface expression as a collapsed or buried wall. If the continuation is real, its geometry will matter. A constructed wall might maintain a consistent width, direction, and relationship to the terrain. It could turn at a corner or connect with another feature. A natural ridge may follow the internal structure of the granite and vary with erosion. Researchers should map not only the line that appears to continue Sage Wall, but every comparable line nearby. Selecting one ridge because it fits the expected plan can make the proposed complex seem more organised than the full landscape actually is. A complete map may reveal a unique structure, or it may show many parallel features produced by regional jointing. The idea of a second wall running parallel up the mountain is especially appealing, because two lines suggest enclosure or planning. One straight rock face can be an unusual fracture. Two matching faces separated by a consistent distance begin to resemble architecture. Yet parallel joint sets can also divide a granite mass into repeated ridges. Erosion may remove the weaker material between them, leaving lines that appear intentionally spaced. The evidence becomes convincing only if the supposed second wall shares details expected from construction and does not simply follow the same geological controls as the first. Voids would be another important target. A buried chamber, passage, or gap between placed blocks could produce a strong radar response because air and surrounding material have very different electromagnetic properties. Natural fractures and cavities can do the same. Granite landscapes contain openings created by block movement, erosion, and weathering. A detected void would therefore require confirmation of shape and context. A rectangular cavity connected to repeated structural lines would be more suggestive than an irregular opening along a fracture. Safety would also become a concern, since any hidden space beneath large unstable blocks should not be entered or excavated casually. Even mysteries have building regulations once several tons of granite are overhead. The underground evidence currently supports continued investigation, but it does not establish a buried megalithic foundation. A reflector has reportedly been observed, possible depth has been discussed, a probe found no stone within 4 feet at one location, and surface mapping has encouraged the idea that the formation continues beyond its obvious end. Each point is worth recording. Together they show that the visible wall does not provide the whole geological picture. They do not yet show that the missing picture contains architecture. That may feel like an unsatisfying position, but it is a productive one. The strongest mystery is not that radar has found a secret flaw. It is that the contact beneath Sage Wall remains insufficiently identified. The next useful result could favour either explanation. If further surveys map a continuous natural rock boundary tied to regional fractures, the buried foundation claim may fade. If targeted work reveals placed blocks on prepared ground, the importance of the site would increase immediately. The investigation does not need a predetermined ending. It needs measurements clear enough that different researchers looking at the same data reach similar conclusions. For the moment, the soil remains in place, preserving whatever relationship lies between the visible granite and the mountain below it. The wall may descend as solid bedrock, as separated natural blocks, as collapsed material, as arranged masonry, or as a complicated mixture of these. The instruments have detected contrasts, but the contrasts have not yet identified their own cause. As attention moves away from depth and toward the physical behaviour of the granite, another set of claims begins to gather around the site. Compasses and electromagnetic instruments have reportedly produced unusual readings. Mineral analysis has raised questions about the stone's composition, and several crashed drones have been added to the story, which is an impressive amount of responsibility to place on a mountain before examining what magnetic minerals normally do. The magnetic claims surrounding Sage Wall begin with measurements taken during an electromagnetic survey of the formation and the ground nearby. According to the Sage Mountain Centre, the survey recorded strong magnetic and conductive responses that the owners regard as anomalous. They have also wondered whether spikes shown in their granite analysis charts correspond with the magnetometry results. Alongside those instrument readings, they report that 6 drones crashed near the site over a period of 3 years, apparently after experiencing signal disruptions. Visitors have also described physical sensations or a feeling of unusual energy while standing beside the granite. These observations have encouraged several interpretations ranging from a natural concentration of magnetic minerals to the suggestion that Sage Wall was deliberately positioned or engineered to use electromagnetic properties. The owners clearly identify several of these statements as personal takeaways from the research, rather than settled scientific conclusions, which is an important distinction when evaluating what the measurements actually show. The word magnetic can make a rock sound more unusual than it is. Granite is often described casually as a pale, non-magnetic building stone, but granitic rocks are mixtures of minerals rather than one uniform substance. Some contain magnetite, an iron oxide that responds strongly to magnetic fields. Others contain smaller amounts of magnetite, related iron-bearing minerals, or mineralized veins that create local changes across a single outcrop. USGS studies of granitic bodies have found that magnetic susceptibility is largely controlled by the amount of magnetite and by the iron content and oxidation history of the rock. Measurements can vary considerably across a batholith, and even within the same exposure. A small magnetite-rich vein can produce a noticeable local response while the surrounding granite remains much weaker. Finding magnetic variability in granite is therefore not evidence of ancient technology by itself. It may simply reveal that the rock is mineralogically complicated, which granite often is when inspected more closely than a kitchen worktop. Magnetic susceptibility has a specific meaning. It describes how readily a material becomes magnetized when it is placed within an external magnetic field. It is not the same as saying that the rock is acting as a powerful permanent magnet, generating energy, transmitting information, or interfering with electronics across a large area. Remnant magnetization is another property, referring to magnetism retained by a rock after the external field or geological process that produced it is gone. Electrical conductivity is different again. It concerns how readily electrical current can move through a material. Electromagnetic surveys may respond to several properties at once, including conductivity, dielectric behavior, and magnetic susceptibility. The instrument records changes in the response of the ground, and those changes must be interpreted in relation to mineral content, fractures, soil moisture, groundwater, depth, and the geometry of the survey. An electromagnetic anomaly is not an object with a known identity. It is a measurement that differs from its surroundings and requires an explanation. Conductivity can also change without anything artificial being present. Fresh dry granite is generally resistant to electrical flow, but fractured or weathered granite may contain water, clay minerals, dissolved ions, or mineralized material that changes its bulk electrical behavior. USGS research has found that the electrical properties of granite can be strongly influenced by the amount and chemistry of free water within it. The decomposed granite and organic soil around Sage Wall may also respond differently from the more solid blocks. A survey crossing from moist soil to exposed rock, then over a fracture containing water or altered minerals, could record a sharp change. This would be genuinely useful geological information. It might help locate hidden fractures, mineral veins, weathered zones, or buried contacts. It would not automatically show that the wall was designed to conduct electricity, or that prehistoric builders understood the anomaly. The location matters because Sage Wall belongs to the Boulder Batholith, a region already known to contain substantial geological and mineral variation. The USGS has conducted high-resolution airborne magnetic and radiometric surveys over the Boulder Batholith and nearby areas to improve understanding of its geology and mineral potential. Earlier aeromagnetic mapping also identified broad variations across the batholith. This does not tell us the exact magnetic properties of Sage Wall, but it demonstrates that magnetic mapping is a normal and useful way to study the region. A local spike at the wall would need to be compared with other granite outcrops formed within the same intrusive system. Without that comparison, calling the result abnormal may simply mean it was higher than the point measured immediately beside it, not higher than the range expected across the wider batholith. A proper magnetic study would begin by stating exactly what instrument was used, what property it measured, the units of measurement, the height and orientation of the sensor, and the spacing between readings. Researchers would repeat measurements along a recorded grid and return to selected points to test whether the values were stable. They would survey nearby granite formations at similar elevations and with similar exposure. They would note metal objects, vehicles, phones, fencing, power equipment, and anything else capable of influencing the instrument. Samples from high and low zones could then be examined for magnetite, iron-bearing minerals, veins, weathering products, and differences in texture. A strong result would be one that could be repeated by another team using comparable equipment. A coloured map with a bright spike is visually effective, but the spike becomes scientifically useful only when its scale, baseline, uncertainty, and geological cause are understood. Variation within one outcrop also means that a small number of measurements can be misleading. USGS work on crystalline igneous rocks found that magnetic susceptibility distributions can be highly variable and strongly non-normal, with researchers taking dozens or more than 100 measurements on individual outcrops to understand the pattern. In such settings, an average may hide important zones, while one unusually high point may exaggerate how distinctive the entire formation is. This is particularly relevant at Sage Wall because the construction claim concerns the whole wall, not one mineral-rich patch. If only a few portions are strongly magnetic, those zones may represent natural veins or inclusions. If every supposed block shares an unusual and consistent magnetic signature that differs from attached bedrock and nearby boulders, the result would be more interesting, though it would still need a geological explanation before a technological one. The granite samples analysed for the property owners reportedly came from upper and lower portions of the wall. Their summary says the samples appeared mineralogically similar, while the darker upper surface was likely affected by greater weathering and exposure. They also wondered whether peaks in the analysis might relate to the magnetic readings. That is a reasonable question, but X-ray diffraction and magnetic susceptibility do not provide the same type of information. X-ray diffraction identifies crystalline mineral phases in a sample, while magnetic measurements record the physical response of the material. A mineral present in a small quantity may have a large magnetic effect, while producing a less dramatic signal in a bulk mineral analysis. Sampling location is therefore critical. A piece collected several feet from the strongest reading may not contain the material responsible for it. To connect the tests, samples would need to come directly from mapped magnetic zones and from matched control zones. The reported drone crashes are memorable because they seem to turn an invisible anomaly into a visible event. 6 damaged drones sound more persuasive than a line on a technical chart, particularly to anyone who has watched a machine fly confidently toward a tree after being given perfectly reasonable instructions. Even so, the crashes cannot be attributed to Sage Wall's magnetism without flight records and controlled testing. Consumer drones depend on several systems, including satellite navigation, an inertial measurement unit, a compass, radio links, software, batteries, and the pilot's view of nearby obstacles. Mountain terrain can block communication, trees can interfere with visual control, and a compass can be affected by local magnetic material or by metal carried with the aircraft. A drone may also lose positioning accuracy without losing the radio connection. The cause of each crash would need to be reconstructed from its logs rather than inferred from where it landed. If compass errors occurred repeatedly in one tightly defined zone beside the wall, that would support the presence of a local magnetic disturbance. Researchers could test this without risking another aircraft. They could carry calibrated magnetometers and several ordinary compasses along fixed paths, recording the position and orientation of each deviation. The survey could be repeated at different heights and at control sites nearby. If the effect weakened predictably with distance from a particular block, samples from that block could be analysed. If no repeatable field disturbance appeared, the drone story would remain an anecdote rather than a measurement. Either result would be useful. There is no scientific requirement that every unusual claim end with a broken propeller. The reports that visitors feel energy at the wall belong to a different category. Personal sensations can be sincere, meaningful, and worth recording as part of the site's social history, but they cannot identify a physical field without controlled measurements. People may feel calm, pressure, tingling, disorientation, warmth, unease, or excitement in response to altitude, expectation, temperature, exertion, sound, sunlight, landscape, and many other factors. Someone who has climbed uphill while thinking about an ancient magnetic structure is not entering the site under neutral conditions. This does not mean the experience is false, it means that an experience and its proposed cause are separate questions. Instruments can test magnetic and electrical properties. They cannot confirm that every reported sensation came from those properties. Even if sage wall proves more magnetic than nearby granite, the finding would not establish human construction. Natural builders had no need to transport the rock into a magnetic zone because the magnetic minerals formed within the rock itself. A prehistoric construction theory would need to show that separate blocks were selected according to magnetic properties, moved from identifiable sources, and arranged in a pattern that used those properties deliberately. Perhaps alternating stones would show different polarities, or a repeatable field would correspond with an architectural feature. No publicly established evidence of that kind has yet been presented. The magnetic observations currently support the much narrower conclusion that parts of the site may have physical properties worth mapping in greater detail. The winter solstice claim moves the discussion from the minerals in the wall to its direction across the landscape. Sage Mountain Center has published three-dimensional models and video showing the winter solstice sunrise in relation to Sage Wall. Its main research page states that the wall is aligned with the rising sun at the winter solstice. On December 21st, 2025, the owners went further in a public update, saying they were confident that the wall was perfectly aligned with the winter solstice sunrise. The claim is important because deliberate astronomical orientation is found at confirmed archaeological sites around the world, including structures in North America. If Sage Wall were shown to be human-built and deliberately aimed at a significant solar event, that would provide information about its possible purpose. At present, however, the published claim comes from the site owners and has not been accompanied on the main page by a peer-reviewed archaeo-astronomical analysis setting out the full measurement method and statistical test. The first problem is defining what aligned means. A long wall has at least two obvious directions. Its length defines an axis pointing toward one end and away from the other. Its face defines a perpendicular direction. An observer might stand at one end and watch the sun rise along the wall, stand in front and see sunlight strike the face, or choose a position where the sun appears over a particular block. Each is a different alignment. The viewing location must be fixed because moving a few meters can change the apparent relationship between nearby stone and a distant horizon feature. The target must also be specified. Is it the center of the solar disk, its first visible edge, the point where it clears a mountain ridge, or the moment direct light reaches a chosen surface? Without those definitions, several observers can agree that the sunrise matches the wall while measuring different events. Astronomers describe the direction of an object with azimuth, measured around the horizon from true north, and its height with elevation or altitude. The apparent position of sunrise depends on latitude, date, atmospheric refraction, the size of the solar disk, and the height of the local horizon. Standard sunrise calculations usually refer to an ideal or astronomical horizon, but Sage Wall sits among mountains. The sun may be geometrically above the level horizon while remaining hidden behind a ridge. Its first visible appearance can therefore occur at a different azimuth from the standard calculated sunrise. A serious alignment study must measure the actual skyline from the proposed observation point and determine where the sun's upper edge, center, or full disk becomes visible. NOAA and the US Naval Observatory define azimuth and sunrise precisely because small differences matter when a claim depends on direction. The winter solstice occurs when the sun reaches its most southerly position in the annual cycle as seen from the northern hemisphere. Near that date, the sunrise position changes slowly from one morning to the next. To an observer watching without survey equipment, the sun can appear to rise in almost the same place for several days. This is the origin of the word solstice, referring to the impression that the sun stands still before reversing direction. A visually convincing match on December 21st may therefore remain almost as convincing on December 20th or December 22nd. That does not weaken a genuine ancient alignment, but it affects claims of perfect precision. Researchers must state the angular width of the proposed target and the range of dates on which the sun would appear within it. The wall itself is not an infinitely thin line. The property owners report that a three-dimensional analysis enclosed about 197 feet of its face within a box approximately 4 feet 3 inches thick. That may show that the surface is relatively planar, but a plane of that thickness provides a range of possible directions rather than one exact azimuth. Irregular edges, uncertain endpoints, and different choices of best fit line can shift the result. The uncertainty should be calculated and displayed. If the measured wall direction is, for example, within a fraction of a degree of the observed sunrise direction, that would be more precise than a match within several degrees. The actual published value, measurement uncertainty, horizon profile, and selected viewing line are needed before the word perfect can be assessed independently. There is also a problem of multiple choices. A long natural feature can be compared with winter solstice sunrise, summer solstice sunrise, winter solstice sunset, summer solstice sunset, the equinoxes, lunar extremes, bright stars, prominent peaks, valley openings, or true cardinal directions. It can be measured along its face, across its face, from either end, from an entrance, from its centre, or from one specially selected block. The more targets and viewing positions considered after seeing the formation, the greater the chance that one will produce an appealing match. Statistical research in archaeoastronomy warns that selection bias can create misleading alignments unless criteria are defined consistently and alternative possibilities are included. A successful match selected from many unreported attempts is less significant than a prediction tested before the observation. This is why archaeoastronomers rarely rely on geometry alone. Clive Ruggles, a leading researcher in the field, has emphasised that the existence of an astronomical alignment does not by itself prove that the alignment mattered to the people who built or used a site. Archaeological context is required. At a confirmed structure, researchers can examine entrances, construction phases, repeated orientations, associated symbols, cultural traditions, and comparable sites from the same society. A single wall pointing approximately toward a solstice event may be intentional, coincidental, practical, topographically controlled, or the result of choosing the most favourable line after measurement. Establishing credibility requires more than showing that the sun can be photographed near an edge. Confirmed solar orientations in North American archaeology are supported by more than the position of the sun. At sites such as Aztec ruins and Hopewell earthworks, the alignments belong to demonstrated human constructions, with documented archaeological contexts, construction histories, and wider cultural patterns. Researchers can study how walls, enclosures, sightlines, and repeated monuments relate to solar or lunar events. Sage Wall has not yet crossed the first threshold, because its status as a constructed feature remains disputed. An astronomical alignment cannot prove the wall was built unless natural geological orientation has first been considered. A naturally fractured granite face can point toward a solstice sunrise by chance, just as a stream, road, ridge, fence, or bedroom window can. The geological alternative is straightforward enough to test. If the wall's direction follows a major joint or fracture set within the boulder batholith, then its orientation may have been controlled by regional stress rather than astronomy. Researchers should measure the wall's azimuth and compare it with fractures across nearby outcrops. If many granite faces share the same direction, the solstice match becomes less distinctive. If Sage Wall differs sharply from the surrounding structural pattern and has an orientation not easily explained by slope or jointing, the result becomes more interesting. The comparison must include all major exposures rather than only those that resemble walls, because natural features that point elsewhere are part of the probability calculation. A strong solar study would select fixed observation points and permanent reference marks. Survey-grade instruments would measure the wall, true north, the local horizon, and the exact position where the sun first becomes visible. Observations would be repeated on several mornings around the solstice, with weather and atmospheric conditions recorded. Computer modelling would calculate the expected position of the sun and show the effect of refraction and horizon elevation. Researchers would state whether the proposed line follows the wall's length, its normal direction, or a sightline between specific stones. They would then compare the result with alternative astronomical targets and with the orientation of nearby geological features. The complete method and measurements would be published so that another team could repeat them. Even a precise solstice alignment would leave the question of intention open. To support intentional design, investigators would want a clearly defined viewing place, a marker or opening that frames the sun, and evidence that the wall's builders could have selected another orientation but chose this one. Repeated related features would help. Perhaps a second line would point toward the summer solstice, or an entrance would admit light at a specific date. A cultural context showing interest in seasonal solar observation would be stronger still. Without such evidence, the alignment may be real as geometry but uncertain as history. The solstice would have been useful to many human societies. Tracking the annual movement of the sun can help organise seasonal gatherings, hunting, travel, food collection, ceremonies, and later agriculture. Ancient people did not require modern instruments to notice where the sun rose at the shortest and longest days. Careful observation over several years would be enough. There is therefore nothing implausible about prehistoric people in Montana understanding the solar cycle. The problem is not whether they had the intelligence to align a structure. The problem is whether Sage Wall is that structure, and whether the measured relationship was deliberately created. Magnetism and solar orientation occupy a powerful place in the Sage Wall story because they suggest function. Large blocks and straight seams may show how something was built, but magnetic properties and a solstice direction invite people to ask why. Perhaps it was a calendar, a ceremonial boundary, an energy device, or part of a larger complex. Once a possible purpose enters the discussion, disconnected features begin to look coordinated. The dark upper stones, the compass readings, the sunrise, the buried reflector, and the projecting knobs can all be fitted into one technological story. That story may eventually prove partly correct, but connecting unexplained details is not the same as demonstrating a system. At present, the magnetic readings are compatible with natural variations in mineral content, weathering, moisture, and fractures within a granitic batholith. The drone crashes remain unverified as magnetic events without technical logs and controlled tests. The winter-solstice relationship appears to be a genuine observational claim made by the property owners, but its precision, statistical significance, and intentionality have not been established through a published independent archaeastronomical study. Neither subject should be dismissed, because both can be tested more rigorously. Neither currently requires an advanced prehistoric technology. That leaves the artificial interpretation in a demanding position. Its strongest case cannot depend on any one feature. It must combine the wall's geometry, the apparent block boundaries, the surface marks, the underground contacts, the geophysical readings, and the orientation into a coherent construction history. It must explain who could have organised such work, what methods they may have used, why no accepted cultural material has yet been found, and how a monument of this scale could disappear from the archaeological record. Those difficulties have not prevented supporters from proposing a lost megalithic complex. They have instead become part of the argument that the builders belong to a period of human history that conventional archaeology has not yet recognised. The case for a lost megalithic complex begins with a simple observation. Sage Wall does not look like an ordinary pile of loose stones. It presents a long exposed face made from very large granite masses, some with angular outlines and narrow divisions that resemble joints between blocks. Certain sections appear nearly planar, and the most regular portions seem to follow a common direction for a considerable distance. Rounded projections have been compared with bosses left on worked masonry, while depressions have been compared with cut marks created by people at confirmed archaeological sites. Surveys have reportedly detected underground reflectors and unusual electromagnetic responses, and the wall has been described as aligned with the winter-solstice sunrise. When these observations are placed together, supporters argue that coincidence becomes increasingly difficult to accept. One straight face might be natural, one polygonal block might be natural, one knob, one hollow, or one magnetic reading might also be natural. The construction theory gains its force by treating all of them as parts of the same system. From that point of view, Sage Wall is not merely an unusual granite exposure. It is the visible edge of a larger design whose remaining features are damaged, buried, or still waiting to be recognised. The Sage Mountain Centre openly describes the formation as megalithic, and has made reports from several non-invasive investigations available while stating that research is continuing. The published material, however, does not yet identify builders, a date, or an archaeological culture associated with the formation. The phrase, builders before history, can be misleading unless we define it carefully. Prehistory does not mean a period before people were intelligent, organised, or technically capable. It simply refers to periods before written records were available for a particular place in society. People lived across North America for thousands of years before European-style written histories appeared, and archaeology has documented complicated systems of travel, hunting, trade, settlement, ceremony, art, and landscape management. Montana alone contains a long record represented by camps, bison kill sites, stone tools, teepee rings, cairns, rock art, bone tools, pottery, and other cultural materials. The Bureau of Land Management describes more than 11,000 years of archaeology in Montana and the Dakotas within its collections, while individual places such as Pompey's Pillar preserve evidence of repeated indigenous use extending over many millennia. The absence of writing therefore tells us nothing about the ability of ancient people to observe the sky, organise labour, or work stone. It only means that their activities must be reconstructed through physical remains, oral histories, environmental evidence, and careful comparison. Our understanding of the first human presence in the Americas has also changed significantly. For much of the 20th century, the Clovis culture, dating to roughly 13,000 years ago, was often treated as the earliest secure archaeological horizon across much of North America. That view has weakened as earlier sites and new dating evidence have accumulated. Human footprints at White Sands National Park in New Mexico have now been supported by several independent dating approaches, placing people there between about 21,000 and 23,000 years ago. The result matters because it demonstrates that archaeology can revise a major timeline when the evidence is strong enough. The White Sands case did not succeed because the prints looked old, or because someone announced that conventional history was wrong. The impressions occurred in identifiable sediment layers. Researchers recorded their geological context. Several kinds of material were dated. Criticisms of the original dating method were tested, and additional work supported the age range. The accepted picture changed because a claim was converted into measurements that other specialists could examine. Montana itself has contributed important evidence to the study of early Americans. The Anzick site contained the remains of an infant associated with Clovis artifacts and red ochre, dating to about 12,600 years ago. Genetic research showed that the child belonged to a population closely related to the ancestors of many present-day indigenous peoples of the Americas. The importance of Anzick does not come from one unusually shaped stone or a visual comparison with another continent. It comes from the association of human remains, diagnostic tools, secure dating, excavation context, and genetic evidence. Multiple lines of evidence support the same historical interpretation. This is the standard a proposed megalithic complex in Montana would eventually need to approach. The claim would not have to resemble Anzic in every detail, but it would need comparable connections between the stones, the people who worked them, and the time when the work occurred. Supporters of Sage Wall sometimes argue that a structure of great age may have lost precisely the evidence archaeologists expect to find. Tools could have been taken away, wooden equipment could have decayed, exposed camps could have eroded, and sediment could have buried occupational surfaces. Later tree growth, frost action, earthquakes, and slope movement might have disturbed the original arrangement. If the builders occupied the site only during construction or seasonal ceremonies, they may have left fewer domestic remains than a permanent settlement would. These are all possible preservation problems. Archaeologists regularly work with incomplete sites where most organic material has vanished and only a small portion of the original activity survives. A lack of pottery would not be surprising if the work predated pottery in the region, and the absence of metal would not show that stone construction was impossible. Ancient builders in many places moved and shaped large stones without engines, steel tools, or written engineering manuals. Human patience is a powerful technology, especially when no one has invented email meetings yet. Preservation cannot, however, become a universal explanation for every missing piece of evidence. If a theory proposes that people quarried, shaped, transported, positioned, and maintained hundreds of tons of granite, the activity should have affected the surrounding landscape. Detaching stone creates fractures, discarded pieces, broken tools and working surfaces. Shaping granite produces chips, crushed grains, and waste material. Moving large blocks requires cleared routes, sledges, rollers, levers, ropes, ramps, or some other mechanical system. Feeding and organising a workforce creates hearths, food remains, camps, pathways, storage areas, and repeated traffic. Preparing a foundation disturbs soil and changes the order of deposits. Not every trace must survive, but it becomes difficult to argue that all of them disappeared while the wall itself remained visible. A convincing loss complex theory should predict where remnants of these activities are most likely to survive, and then test those locations. The first practical question is whether the supposed blocks were ever separate from the bedrock. If they remain attached behind the visible face, then they were not quarried elsewhere and carried into position. People might still have shaped the exposure, but the proposed achievement would be closer to cutting or modifying a natural granite ridge than constructing a freestanding wall. That would still be significant, particularly if deliberate surfaces or symbols could be demonstrated, but it would be a different kind of site. If the blocks are fully detached, the next question is whether they moved. A naturally fractured block can remain almost exactly where it formed. It does not require workers, transport equipment, or a reason for placement. Evidence of movement could include stones rotated away from the local joint direction, blocks resting on packing material, unnatural gaps beneath them, prepared contact surfaces, or rock types traced to another source. None of those relationships has yet been established publicly for Sage Wall. The extraordinary size of the granite is often presented as evidence of advanced technology. This reasoning contains a small difficulty. If the wall is built, the size creates a major engineering problem for the construction theory. If the wall is natural, the size is not difficult to explain because the boulder batholith is a vast body of granite that was already present. Nature did not need to lift a block and carry it uphill. The block could have formed when fractures divided an existing mass. Supporters sometimes answer that the difficulty of moving the stones proves the builders possessed methods unknown to us. That possibility cannot be ruled out simply because the methods would be impressive, but an unknown technology should not be introduced before evidence of movement has been found. Otherwise, the reasoning becomes circular. The blocks must have been moved because they form a wall, and the wall must have been built because an advanced culture could have moved the blocks. Ancient people did not need mysterious machinery to accomplish difficult stonework. Large construction can be achieved by combining simple tools with planning, leverage, friction reduction, prepared slopes, and a large labour force. Wooden levers can multiply force, ropes can distribute effort, sledges can move loads across prepared surfaces, repeated pecking with harder stones can shape a face gradually. Fire and cooling can help weaken some rock, though controlling the result in granite would be difficult. Sand and water can assist abrasion. These methods are slow, but prehistoric construction projects were not limited to the timetable of a modern home renovation, where everyone becomes worried after the kitchen has been unavailable for 10 days. The real question is not whether ancient people were capable of solving mechanical problems. It is whether sage wool preserves evidence that such solutions were used there. The proposed builders are rarely identified consistently. Some descriptions refer only to an unknown prehistoric culture. Others suggest a civilization far older than the indigenous cultures recognized in the regional archaeological record. More speculative versions connect sage wool with a worldwide megalithic tradition, arguing that polygonal blocks and raised knobs resemble sites in South America, Egypt, Japan, and other regions. These comparisons are visually powerful, but they skip several steps. Similar stone shapes do not establish contact between distant societies. Polygonal forms can result from deliberate masonry, but they can also result from natural fracturing. Raised bosses can be left by workers, but resistant patches can remain through differential weathering. Even when two confirmed structures use similar techniques, the similarity may reflect independent solutions to the same physical problem rather than one global culture. A worldwide building theory would require evidence beyond shared appearance. Researchers would look for matching construction sequences, comparable tool traces, related measurement systems, transport methods, symbols, artifacts, dates, and perhaps biological or genetic evidence of contact. The sites would need to belong to overlapping periods. A resemblance between a Montana outcrop of unknown status and a wall built thousands of years later on another continent cannot establish a connection. Architecture is full of repeated solutions because gravity behaves with remarkable consistency wherever builders encounter it. Stones are placed with broad faces down, gaps are filled, corners interlock, and walls tend to stand more successfully when they are not leaning toward the people who built them. The possibility of an unknown local tradition is more restrained and therefore easier to test. Human history in the northern plains and Rocky Mountain regions includes many mobile and seasonally organized communities whose structures were often made from wood, hide, brush, earth, and smaller stones. Archaeological sites in Montana preserve teepee rings, camps, hunting features, cairns, rock art, tools, and food remains. These records demonstrate long occupation and detailed knowledge of the landscape, but they do not currently include a recognized tradition of constructing enormous fitted granite walls comparable with the strongest interpretation of sage wool. This does not mean such a tradition could never be discovered. Archaeology does not possess a complete inventory of every activity performed in the past. It means that sage wool would represent a major departure from the currently documented construction record and would therefore require correspondingly clear evidence. There is an ethical problem when an unknown civilization is imagined in a landscape with known indigenous histories. Alternative history discussions sometimes present large or sophisticated features as things local peoples could not have made. The builders are then described as a vanished race, outsiders from another continent, or members of a superior civilization erased from history. Such claims have often been used to separate indigenous communities from their own heritage. Sage wool does not currently have an accepted cultural attribution, so it should not be assigned casually to any group, known or unknown. If evidence of human construction emerges, consultation with tribal historic preservation officers and communities connected to the region would be essential. Montana's preservation system explicitly includes tribal preservation offices, and federal archaeological work recognizes that cultural places may remain significant to living peoples. This consultation would not be a ceremonial step added after the technical work. Indigenous knowledge can include place names, travel routes, resource areas, sacred landscapes, and accounts of how particular formations were understood or used. Such information would not automatically prove that Sage Wall was built, just as an absence of remembered construction would not prove that it was natural. Oral traditions have their own histories, purposes, and rules for sharing. They must not be treated as convenient evidence to be extracted for an online mystery. The point is that any investigation claiming to rewrite the human history of Montana should engage seriously with the people whose histories are already present there. The function of the proposed complex is another unresolved issue. A wall nearly 300 feet long might have served as a boundary, terrace, defensive structure, ceremonial platform, astronomical marker, retaining wall, or part of a larger enclosure. Each function predicts different associated features. A defensive wall should relate to access routes, vulnerable approaches, and protected space. A retaining wall should hold material on one side and respond to the slope. An astronomical installation should contain a stable observation point and a carefully defined sight line. A ceremonial platform might be associated with cleared surfaces, deposits, offerings, paths, or repeated use. A building wall should connect with corners, floors, entrances, or parallel walls. At present, there is no widely accepted architectural plan showing how Sage Wall fits into a coherent complex. Possible ridges and alignments have been identified in LiDAR imagery, but the owners state that specialist interpretation remains incomplete. Without a clear function, every unusual feature can be given several explanations. A projecting knob may become a lifting point, ornament, energy component, or unfinished surface. A cup mark may become a socket, ritual hollow, tool mark, or astronomical marker. A magnetic zone may become part of an energy system. A solstice direction may become a calendar. The buried reflector may become a foundation or underground chamber. The problem is not that any one interpretation is impossible. The problem is that the interpretations can be changed to fit the feature after it is discovered. A testable model should state in advance what additional evidence must exist. If the complex served as an astronomical centre, where should the observing position be? If it used magnetic properties, what measurable arrangement should the blocks display? If the knobs were used in lifting, where should they occur on the blocks, and what damage should ropes or tools have left? The strongest artificial case would begin by reducing its claims rather than expanding them. It would not need to prove a global civilization, lost electrical technology, giant builders, or a date before the last ice age. It would begin with one manageable question. Is any portion of Sage Wall demonstrably modified or placed by people? A single securely identified work surface could justify more investigation. One detached block resting on prepared fill could change the interpretation of the formation. A concentration of granite working debris in an undisturbed layer would be important. Repeated percussion marks confirmed through microscopy would be more useful than 100 broad visual comparisons. Archaeology often advances through small details that establish human action before larger historical conclusions are attempted. Dating would then become essential. There is no reliable way to determine the construction age merely by looking at the size of the blocks or the amount of weathering. A wall can look ancient after a few centuries in a harsh environment, while a protected surface can remain fresh for thousands of years. The granite's geological age of tens of millions of years says nothing about when a person might have altered it. Researchers would need datable material from a secure relationship with any artificial feature. Charcoal sealed beneath a placed block, sediment within a foundation trench, organic remains on a floor, or material trapped during construction could provide possible dating targets. Each sample would need careful evaluation because roots, rodents, water, and later visitors can move material into older deposits. An old piece of charcoal near the wall would show that something burned there at an earlier time. It would not prove the wall was built during the same event unless the stratigraphic relationship was clear. The white sands footprints provide a useful comparison because they show what happens when a claim genuinely challenges an established timeline. The first dates were questioned partly because the aquatic seeds used for radiocarbon dating might have absorbed old carbon from the water, making them appear older. Researchers did not answer by accusing critics of refusing to rewrite history. They collected pollen, used additional dating methods, studied the sediment, and produced independent age estimates. The controversy did not disappear through confidence. It narrowed through repeated measurement. A sage wall construction claim would benefit from the same process. Criticism would not be evidence of suppression. It would identify the measurements most likely to persuade specialists if the hypothesis is correct. Claims that archaeology would refuse to recognise the site underestimate how significant a confirmed discovery would be. A prehistoric megalithic structure in Montana, especially one predating known monumental traditions in the region, would generate enormous professional interest. It would offer research opportunities in technology, migration, social organisation, astronomy, geology, and indigenous history. Archaeologists may be cautious because mistaken claims about natural formations are common, but caution is not the same as opposition to discovery. The discipline is built around finding things that were not known before. The requirement is that a claim must be documented well enough to survive inspection by people who did not begin with the same conclusion. There are practical reasons the evidence remains limited. Sage Wall is on private land, and the owners are responsible for protecting it while managing access. A full archaeological project requires funding, permits where applicable, specialists from several fields, laboratory analysis, consultation, conservation planning, and years of work. Non-invasive surveys are a reasonable first stage, but they cannot answer every question. Excavation, if undertaken, would need to avoid destabilising enormous blocks or destroying subtle evidence. The site has also become popular online, increasing the risk of contamination, unauthorised scraping, misplaced objects, and visitors unintentionally changing surfaces. By the time a disputed location receives formal study, modern activity may already have created some of the confusing details. The most persuasive version of the lost complex hypothesis therefore remains possible in a narrow sense, but unproven in every important historical detail. It is possible that people modified a natural outcrop. It is possible that buried evidence has not yet been found. It is possible that an unknown construction tradition existed locally and left very few surviving examples. Archaeology has revised major ideas before, and the record of early human presence in the Americas is older and more complicated than scholars once believed. None of those general truths establishes that Sage Wall is artificial. They only prevent us from dismissing the question because the proposed history would be surprising. What currently supports the artificial interpretation is a cumulative visual argument. The blocks look fitted, the face looks aligned, certain surface details resemble worked stone, the formation may continue underground, magnetic measurements have raised questions, and the sunrise appears to relate to its direction. What remains missing is the direct bridge from appearance to human action. There are no publicly confirmed tool marks, no established quarry, no documented transport evidence, no secure foundation trench, no cultural layer, no accepted artifacts associated with construction, no construction date, and no identified builders. The gap between those two lists is where the mystery survives. The case for a lost megalithic complex should not be mocked, because several observations deserve careful study, and the history of the Americas still contains unanswered questions. It should also not be accepted because the alternative would feel less exciting. A natural granite formation can be large, straight, fractured, magnetic, weathered into knobs and hollows, partly buried, and oriented toward a notable sunrise without having been designed. To judge whether that combination is improbable enough to require builders, we now need to examine the geological explanation as a complete process, rather than as a collection of convenient excuses. That means returning to the boulder batholith, the cooling magma that created it, the fractures that divided it, and the long sequence of weathering that may have turned one section of ancient granite into something that looks remarkably like a wall. To understand how sage wall could have formed without builders, we have to begin long before there was a mountainside, a forest, or even a surface on which a wall could stand. The granite belongs to the boulder batholith, a large group of intrusive igneous bodies that formed in southwestern Montana during the late Cretaceous. The main mass is commonly called the Butte granite, although the batholith also contains several smaller intrusions with somewhat different mineral compositions and textures. These rocks began as magma moving into older sedimentary and volcanic formations deep within the crust. They did not erupt onto the surface as a single river of lava and then cool into a wall. Geological and geophysical evidence indicates that the batholith was a thick, intrusive complex assembled over millions of years, with its major bodies extending far below the landscape that is visible today. The ancient fire in this explanation was therefore buried magma, held under pressure and cooling, slowly enough for crystals of feldspar, quartz, biotite, hornblende and other minerals to grow together into coarse-grained rock. The boulder batholith was not created in one brief event. USGS studies describe it as a composite system in which several magmas were emplaced between roughly 81 and 68 million years ago, with some later magmatic and hydrothermal activity continuing in parts of the region. The intrusions were connected with a period of intense tectonic activity, faulting, volcanism, and mountain building in western Montana. Magma entered a crust that already contained very old zones of weakness, some inherited from events more than 1 billion years earlier. Those weaknesses helped control where later faults, joints, mineral veins and intrusions developed. The region surrounding Sage Wall is therefore not a simple lump of featureless granite. It is part of a complicated body that cooled under stress, interacted with older structures, cracked in preferred directions, and was later altered by hot fluids moving through some of those openings. Slow cooling turned magma into solid rock, but solid rock does not remain free of stress. Granite contracts as it cools, and contraction can create fractures. Regional tectonic forces can add another system of breaks. Fault movement can reactivate older weaknesses or produce new ones. The boulder batholith contains joints and veins with repeated orientations, including northeast, east-west and northwest trends documented in the wider Butte region. These directions are not random marks scattered independently through every few feet of stone. They reflect forces acting across large areas. When two or more fracture sets cross, they divide a continuous mass into angular sections. One set can create long vertical faces, another can create cross joints, and a lower angle set can form something that resembles the boundary between courses of masonry. The resulting shapes may be rectangular, trapezoidal or polygonal depending on the angles at which the fractures meet. This is the first major part of the natural explanation for Sage Wall. The apparent blocks may not have been placed beside one another. They may be sections of one larger granite body separated by intersecting joints. From the front, a fracture can look exactly like the seam between two individual stones. Soil, moisture, lichen, shadow, and loose grains can darken that seam, making it appear deeper and more deliberate. If a narrow piece between two joints breaks away, the remaining edges may look fitted. A crack that enters the rock diagonally can create the visible outline of a five-sided block, even when the stone remains attached several feet behind the surface. The geometry looks organised because the forces producing the joints were organised over a broad region. They did not choose the shape of each block, but they did provide repeated planes along which the granite could split. Granite formations elsewhere show how convincing this process can become. The National Park Service explains that vertical fractures combined with lower angle or horizontal fractures can separate granite into large rectangular blocks. At Acadia National Park, tectonic cracking, pressure release, and repeated freezing and thawing in large fractures until the rock developed block-like forms. City of Rock's National Reserve displays jointed granite broken into large masses, with weathering concentrated along the fractures. These places are not exact copies of Sage Wall, and examples from another region cannot prove how one Montana formation developed. They do demonstrate that natural granite can produce edges, corners, slabs, and repeated block shapes without being quarried or assembled. Pressure release may have added another set of weaknesses as erosion exposed the batholith. The granite originally crystallized beneath an immense weight of overlying rock. As uplift and erosion removed that material, pressure on the buried granite decreased. Near the surface, the rock could expand slightly and fracture roughly parallel to the exposed landscape. These fractures are commonly called sheeting joints, and the gradual separation of slabs is associated with exfoliation. The familiar result is often a rounded granite dome peeling in broad layers, but the same general process can also help detach large sheets from steeper faces. In Yosemite, sheeting joints divide granite into slabs that can loosen and fall, while daily heating and cooling can cause existing sheets to open and close by small amounts. Researchers have even documented large granite sheets fracturing during periods of intense heat. None of this means Sage Wall was produced by exfoliation alone. It shows that enormous, relatively flat pieces can separate naturally from a granite mass after exposure. The long face of Sage Wall could therefore represent a fracture-controlled exposure rather than the front of a constructed wall. Erosion may have removed weathered material from one side of a joint while leaving the more intact granite behind it. If the joint continued in a fairly consistent direction, the exposed face would also follow that direction. Additional fractures crossing it would divide the surface into apparent blocks. The result could remain unusually planar for tens or even hundreds of feet, because the original weakness extended through a substantial part of the outcrop. Calling this process random would be inaccurate. The precise location of every broken piece may be difficult to predict, but the larger fracture pattern can be controlled by regional stress and the internal structure of the rock. Once cracks existed, water began working through them. Rain and melting snow entered openings too narrow for roots or loose sediment. Some of that water froze during cold periods and expanded, placing pressure on the fracture walls. The usual description of frost wedging can make the process sound as though one winter night splits an entire cliff with a loud crack. In reality, the effect is often cumulative and depends on the amount of water, the shape of the fracture, the temperature cycle, and the existing weakness of the rock. Repeated freezing and thawing can loosen grains and help widen joints that were already present. USGS research on granite landscapes identifies freeze-thaw cycles, roots, water, gravity, and temperature changes among the physical processes that break exposed rock apart, while observations in Yosemite show that water and seasonal freezing can contribute to the failure of fractured granite. Temperature changes can continue the work even when water is not freezing. Rock surfaces warm in sunlight and cool at night, while material farther inside changes temperature more slowly. Different minerals also expand by different amounts. Over many cycles, these variations can increase stress around existing cracks. Modern monitoring of exfoliating granite has recorded measurable daily movement linked to heating and cooling, and studies have shown that thermal stresses can help cracks grow until slabs become unstable. Montana does not have Yosemite's exact climate or cliff geometry, and the same process should not be transferred to Sage Wall without local measurements. It remains a credible way for exposed granite sheets and blocks to loosen after the main fracture system is already established. Chemical weathering acts more quietly. Granite may appear almost indestructible, but several of its minerals react with water. Feldspar can alter into softer clay minerals, weakening the connections between grains. Biotite and other iron-bearing minerals can oxidize and expand or break down. Quartz generally resists alteration more effectively and may remain after the minerals around it have changed. Water follows joints because those openings provide access to the interior of the rock. Corners where several fractures meet are exposed to chemical attack from more than one direction, so they often weather faster than broad flat surfaces. This process can round block corners, widen seams, produce sandy decomposed granite, and leave harder sections projecting from the face. The USGS describes spheroidal weathering as a process in which groundwater attacks fractured granite below the surface, with corners breaking down first and the remaining blocks becoming progressively rounder. This helps explain why sage wool can contain both sharp-looking geometry and rounded features. The initial joints may have produced angular blocks. Weathering then modified those forms unevenly. A recently exposed fracture surface may remain flat and sharp, while an older corner nearby becomes rounded. A quartz-rich zone may survive as a knob after feldspar-rich material around it turns to clay and falls away. A small mineral weakness can deepen into a hollow. Cavernous weathering can create pits and recesses on granite joint surfaces, while harder ridges remain between them. The wall does not need one process to account for every feature. Its present appearance may record a sequence in which fracturing created the main divisions, chemical alteration weakened selected zones, frost and temperature changes widened cracks, and erosion removed the loosened material. The loose granular material found around weathered granite is often called grus. It forms when the rock loses cohesion and breaks down into coarse sand containing quartz, feldspar fragments, and other mineral grains. A large block may remain solid while the granite beside or beneath it becomes grus. Later erosion can remove part of this softer material, exposing the block as though it had been placed on the surface. Elsewhere, grus may accumulate against the lower face and bury part of the rock. This offers a natural explanation for why sage wool seems to continue into the ground, and why a probe beside the visible face might pass through several feet of loose material without striking solid stone. The block-like mass may be bordered by deeply weathered granite rather than standing on an artificial foundation. City of Rocks National Reserve identifies grus as a primary product of granite weathering and shows how solid outcrops, rounded blocks, joints and decomposed material can occur together in one landscape. Gravity then begins to reorganize what weathering has loosened. A block separated along several fractures may tilt, settle, or move slightly downslope. It does not need to travel far. A shift of a few centimeters can open one seam and close another. A slab can rotate until one edge rests against the block below it, creating a contact that looks deliberately fitted. Smaller pieces can fall from gaps, leaving the larger masses more visible. Soil and decomposed granite can wash into the remaining openings. Over time, the exposed face begins to resemble a wall, assembled from stones even though the pieces have never left the original outcrop. Rockfalls in other granitic settings show that joint patterns control the size and shape of the pieces that detach. Large slabs may fail along one main sheet fracture, while cross joints determine their ends. Tree roots can assist this slow adjustment. Roots commonly enter existing cracks where water and loose material are available. As they grow, they exert pressure and can help separate already fractured rock. A falling tree may pull material from a seam or disturb soil at the base. Roots can also redirect water, retain organic matter, and create local chemical conditions different from those on an open face. This means vegetation can widen some fractures while leaving neighbouring sections relatively unchanged. A line that looks like the collapsed edge of a structure may have been enlarged by a tree, whose roots used the joint long after the granite reached the surface. Erosion does not simply break the wall down, it also reveals it. The batholith formed beneath older rocks and volcanic material. Those overlying formations had to be removed before the granite could appear at the surface. Streams, weather, slope movement and regional uplift gradually stripped the covering away. Once exposed, softer altered zones disappeared faster than stronger granite. A long fracture may have guided drainage or concentrated weathering, allowing material on one side to erode more quickly. The remaining face would then stand above the surrounding ground. What looks like construction upward may actually be erosion downward and outward. Nothing had to raise the blocks into a wall. The landscape lowered around them. The reference to ancient volcanic activity sometimes causes confusion because the boulder batholith is associated with late Cretaceous volcanic rocks. Volcanism did occur in the region, and the batholith was emplaced into and beneath the Elkhorn Mountains volcanics. Later volcanic rocks also occur above eroded portions of the batholith in some areas. The batholith itself, however, is primarily intrusive. Its coarse crystals show that much of the magma cooled slowly underground rather than rapidly at the surface. Describing Sage Wall as naturally formed by volcanic activity is therefore broadly connected to the region's igneous history, but it can give the wrong impression if it suggests that lava erupted and hardened directly into a neat row of blocks. The more accurate sequence involves deep magma emplacement, slow crystallization, tectonic fracturing, uplift, erosion, surface weathering, and gradual exposure. Hot fluids associated with the cooling intrusions also travelled through fractures and created veins and altered zones. The northern boulder batholith contains hundreds of documented veins, including quartz sulfide and chalcedony systems, and the Butte region became famous for mineral deposits controlled partly by faults and joints. Hydrothermal alteration can change the strength, colour, magnetic properties, and weathering behaviour of rock. A mineralised fracture may resist erosion and remain as a ridge, or it may weather faster and deepen into a seam. Iron-bearing minerals can stain the surface. Magnetite and related minerals can create local magnetic differences. This means several features treated as separate mysteries at Sage Wall may share one geological origin. A fracture formed through stress, carried mineral-rich fluid, developed a different composition from the surrounding granite, responded differently to weathering, and later produced both a visible line and an unusual instrument reading. This does not mean a mineral vein has already been shown to explain every magnetic or visual anomaly at Sage Wall. A site-specific study would need to map the strongest readings and compare them directly with mineralogy, fractures, moisture, and surface features. The broader geological record simply makes such an explanation plausible. The boulder batholith is known for structural complexity, hydrothermal alteration, mineral veins, and measurable magnetic variation. An unusual reading within that environment does not begin from a blank page. It begins inside a region where those properties are expected to vary. The winter-solstice orientation may also fit naturally into the fracture story. If the wall follows a regional joint set, its direction was controlled by stress in the crust. That direction might happen to correspond with the sunrise from a particular viewing point. A long natural face provides several possible lines to measure, including its length, its perpendicular direction, its upper edge, and sight lines from either end. Mountains add several possible horizon points where the sun can first become visible. A match can therefore occur without anyone selecting the alignment. The correct geological test would be to measure Sage Wall's orientation and compare it with joints and rock faces throughout the surrounding batholith. If the same direction appears repeatedly in nearby natural exposures, crustal structure would provide a simpler explanation than astronomical design. If Sage Wall alone departs from the local fracture pattern while maintaining a precise constructed geometry, the natural model would need reconsideration. The geological explanation is persuasive because it uses processes known to operate in granite and processes known to have affected the boulder batholith. It does not require a missing population, unknown tools, unrecorded quarries, buried settlements, or a construction tradition absent from the current archaeological record. This advantage is often described through the principle of parsimony. When several explanations account for the evidence, the one requiring fewer unsupported assumptions is generally preferred. Parsimony does not mean that the ordinary explanation must always be correct. It means that extraordinary additions should be introduced only when the observed details require them. At Sage Wall, the natural model can account broadly for the main features. Deep magma produced a large granite body. Cooling and tectonic stress created repeated joints. Pressure release may have produced lower angle fractures and sheets. Intersecting planes divided the rock into angular masses. Water and chemical alteration weakened the edges. Frost, roots, and thermal cycles widened the openings. Gravity shifted or removed selected pieces. Erosion cleared the material in front of a long fracture-controlled face. Differential weathering produced knobs, hollows, rough areas, smooth joint surfaces, and colour changes. Decomposed granite accumulated at the base, partly burying the lower stone. Mineral veins and iron-bearing minerals produced local electromagnetic differences. The orientation followed the internal fracture pattern, with a possible solar match occurring through geometry and selection. That is a coherent explanation, but coherence is not the same as proof. The complete sequence is plausible at the scale of regional geology, yet each proposed step must still be tested at Sage Wall. Researchers would need to show that the apparent block boundaries behave like joints, that the supposed courses connect to natural fracture sets, that the blocks remain attached to bedrock, and that comparable forms occur nearby. Mineral analysis should link knobs, seams, colour changes, and magnetic responses to differences within the granite. Underground surveys should identify weathered bedrock, natural fractures, or grooves rather than prepared foundations. A geological explanation becomes decisive only when it explains the site's most unusual details more accurately than the construction hypothesis. There are several observations that could weaken it. Separate blocks resting on imported or compacted fill would be difficult to explain through intact bedrock weathering. Repeated percussion marks would require human contact. A quarry with matching missing blocks would change the discussion. Stoneworking debris sealed in an old deposit would show that granite was shaped nearby. A clear architectural plan cutting across natural joint directions would reduce the likelihood of accidental alignment. The geological interpretation should not be protected from such discoveries by calling every new feature natural in advance. Its strength comes from being testable. For now, geology provides the most developed mechanism available. It explains how large angular forms can arise without movement, why straight surfaces can extend across great distances, why cracks can repeat at similar angles, why the stone can appear partly buried, and why surface details vary from one section to another. It also places Sage Wall within a known regional history rather than treating it as an isolated object dropped into Montana without context. The formation belongs to an ancient intrusive complex shaped by magma, faulting, hydrothermal fluids, pressure release, weathering, and erosion over tens of millions of years. That history is fully capable of producing structures that look planned even though no plan was involved. The remaining question is whether the natural explanation merely can produce something like Sage Wall, or whether it actually produced this wall. That distinction brings us back to the evidence itself. The geological case is strong where it relies on documented regional processes, but some claims about the exact formation remain based on photographs, limited surveys, and interpretations that have not yet been tested through a full independent field study. The megalithic case is visually compelling, but it lacks the artifacts, tool traces, dating, and construction context needed to identify human work. The final task is therefore not to select the more dramatic story or the more familiar one. It is to place each major claim beside the evidence supporting it and determine what Sage Wall allows us to say with confidence, what remains possible, and what is still missing. After examining the blocks, the seams, the knobs, the cup-shaped hollows, the underground readings, the magnetic claims, the solstice alignment, and the geological history of the boulder batholith, we are left with a question that sounds simple, but is surprisingly difficult to answer. Is Sage Wall a monument or a mountain? The honest answer is that the available evidence does not currently establish it as a human-built monument, but neither does that make the formation unimportant. Sage Wall is a real physical place with measurable features, and several of those features deserve more careful study. What remains uncertain is not whether the granite exists, whether the wall-like face is impressive, or whether people have recorded unusual observations there. The uncertainty concerns how those features formed and whether any part of the site was deliberately modified, arranged, or used by people in the distant past. The strongest argument for construction comes from the way the features appear together. The formation is long, its face can look unusually straight. The granite is divided into large angular masses, some of which resemble polygonal masonry. Certain joints appear narrow enough to suggest fitted blocks. Protrusions on the stone have been compared with bosses on ancient masonry, while shallow depressions have been compared with cup marks. Some surveys have been interpreted as indicating buried continuation beneath the present ground surface. Magnetic measurements have produced local anomalies, and the wall has been described as relating to the winter-solstice sunrise. Considered separately, each observation has a possible natural explanation. Considered together, they create the impression of a designed place. That cumulative impression is the main reason the question has survived. The difficulty is that several uncertain observations do not automatically combine into one certain conclusion. If the block boundaries are natural joints, the knobs are resistant patches left by weathering. The cup-shaped hollows are natural pits. The underground reflector is a change between weathered material and solid rock. The magnetic readings come from iron-bearing minerals, and the solar orientation is coincidental. Then adding them together does not create evidence of construction. It creates a group of geological features that happen to resemble the parts of a structure. The number of observations matters only if they are independent, and if each one is difficult for the natural explanation to account for. This distinction is easy to miss because the construction theory provides a single story that connects everything. Builders selected the site, shaped or placed the blocks, used the knobs during lifting, made the hollows for tools or ceremony, prepared a buried foundation, chose magnetic stone, and aligned the structure with the solstice. Once that story is accepted, every feature appears to confirm it. The geological explanation is less dramatic because it divides the formation into many slow processes. Magma cooled, cracks formed, pressure changed, water entered the fractures, minerals weathered at different rates, frost widened openings, roots added pressure, gravity shifted loose pieces, erosion removed softer material, soil accumulated around the base. Mineral variations affected magnetic measurements. The wall followed a fracture direction that happened to relate to the sunrise from a particular viewing position. It is a longer explanation, but it relies on processes already known to operate in the region. A longer explanation is not necessarily a weaker one. Natural landscapes are often produced by several processes acting in sequence. A valley may require uplift, faulting, river erosion, glaciation, slope collapse, and sediment deposition. No one considers that suspicious merely because several stages are involved. Sage Wall may be similar. Its present form could reflect events separated by millions of years. The granite crystallized deep underground. Regional stresses created fractures. The overlying rock was removed. Surface weathering enlarged the joints. Pieces detached. Soil covered the lower sections. The result seen today may be only the most recent stage in a history that began while the landscape above it did not yet exist. The natural explanation has one major advantage. It begins with the known geology of the site. Sage Wall stands inside a large granite batholith where fractured outcrops, mineral veins, weathered blocks, and long structural trends are expected. The surrounding landscape provides a mechanism for producing the stone without importing material, inventing a quarry or requiring a workforce. The apparent blocks can remain where they formed. Their size is not a transportation problem because no transportation is required. Their angular shapes can follow intersecting joints. Their partial burial can result from soil and decomposed granite collecting around the base. The magnetic variation can reflect mineral content. From this perspective, Sage Wall is unusual, mainly because one fracture-controlled face is especially large, exposed, and visually organized. The artificial explanation has a different advantage. It takes seriously the possibility that appearance may reflect real modification. Human beings have altered natural formations throughout history. They have cut steps into cliffs, deepened caves, carved symbols into boulders, built walls against bedrock, cleared platforms, arranged stones, and used prominent features as ceremonial or practical landmarks. Sage wool does not need to be a completely manufactured structure for human activity to be present. A natural outcrop could have been modified in selected areas. Some hollows could be artificial, while the larger wall remains geological. Stones could have been placed beside the main exposure. A natural alignment could have been noticed and used as a seasonal marker. This mixed possibility is less dramatic than a lost megalithic city, but it may be more realistic than forcing the entire site into one category. At present, no widely accepted archaeological evidence demonstrates that the large granite masses were quarried, transported, or assembled. No secure set of tools has been connected with construction. No published collection of stoneworking debris identifies a nearby production area. No confirmed foundation trench has been exposed. No cultural layer has produced a date for building activity. No recognised architectural plan links the main wall with entrances, floors, corners, or enclosed spaces. No known prehistoric society in the region has been connected to construction on this scale. These absences do not prove that sage wool was never modified by people, but they prevent us from identifying builders or assigning the formation to a lost civilization. The lack of artifacts is one of the most important issues because large construction usually leaves more than a finished wall. Workers break tools, they create stone chips, they clear paths and prepare surfaces, they light fires, eat food, move soil, and leave material in places where it would not naturally occur. A structure may survive while much of the associated evidence disappears, particularly in a harsh mountain environment, but complete disappearance becomes less likely as the proposed project grows larger. If sage wool was part of a vast complex, future research should be able to find some trace of the human activity required to create it. The most decisive evidence might come from the contacts between the supposed blocks. If they remain attached to continuous bedrock behind the visible face, then the formation was not assembled as a wall. Human modification would still be possible, but the blocks would not have been transported and placed. If they are separate, researchers would need to determine whether natural fractures produce that separation, or whether the stones were moved. Prepared surfaces, packing stones, imported fill, rotated blocks, and repeated tool marks would change the interpretation. This is why a small, carefully planned excavation could be more valuable than another collection of dramatic photographs. The important discovery may not be a hidden chamber or an ancient object. It may be a simple contact showing whether one block sits naturally within the mountain or deliberately upon prepared ground. The surface marks also remain testable. A knob that looks like a lifting boss can be examined microscopically to determine whether surrounding material was deliberately removed. A cup-shaped hollow can be mapped in 3 dimensions and compared with naturally weathered pits on nearby granite. Researchers can look for percussion damage, abrasion, repeated dimensions, and patterned placement. If similar knobs and hollows occur across untouched outcrops in the same area, their archaeological importance would decrease. If sage wool alone contains repeated marks with signs of controlled working, the possibility of human modification would become stronger. The magnetic claims require the same local comparison. A high reading is meaningful only when the normal range for the surrounding granite is known. The boulder batholith contains mineral variation, fractures, altered zones, and iron-bearing minerals capable of producing differences across short distances. A magnetic survey should therefore include the wall, nearby outcrops, loose boulders, soil, and known mineral veins. The measurements should be repeated with calibrated instruments and recorded on a detailed map. Drone crashes and personal sensations may be interesting parts of the site's modern story, but they cannot replace controlled measurements. A machine can fail for many reasons, and a person can experience a place strongly without the cause being electromagnetic. The solstice claim also needs a more exact test. A photograph of the sun near the wall on a winter morning can show that a visual relationship exists, but intentional astronomical alignment requires more information. Researchers need a fixed observation point, a defined line through the formation, an accurate horizon profile, a measured azimuth, and a stated tolerance. They also need to compare the chosen direction with other possible directions in the wall and with fracture patterns in nearby granite. If the wall follows a common regional joint orientation, the solar relationship may be coincidental. If it cuts across the local geology and contains a clear viewing position designed around the sunrise, intention becomes more plausible. Even then, archaeological context would be required to show that people created or used the alignment. This may sound like science removing the mystery one measurement at a time, but good investigation does not make a place less interesting. It makes the questions more precise. Instead of asking whether the wall feels artificial, we can ask whether the blocks are attached to bedrock. Instead of asking whether the knobs resemble ancient masonry elsewhere, we can ask whether they preserve traces of carving. Instead of calling a radar response a foundation, we can ask what material boundary produced it. Instead of saying the rock has unusual energy, we can measure the magnetic field and identify the responsible minerals. Instead of accepting or rejecting the solstice claim by appearance, we can calculate the exact relationship. The outcome may not satisfy everyone. If geological work eventually shows that Sage Wall is entirely natural, some visitors will continue to see architecture in it. Visual impressions can be stronger than technical reports, especially when the stone is large and the explanation depends on processes too slow to observe directly. If archaeological work finds a few signs of human modification, others may immediately expand those signs into proof of a continent-spanning civilization. Evidence rarely prevents speculation. It only gives us a firmer place from which to judge it. There is also a difference between an unexplained feature and evidence for a specific explanation. Suppose one cup-shaped hollow cannot be classified confidently. That does not mean it was made by builders. It means its origin remains uncertain. Suppose a reflector beneath the wall cannot be identified. That does not make it a foundation. It means more information is needed. Suppose the alignment is more precise than expected. That does not identify who selected it or when. Uncertainty should remain attached to the observation rather than being transferred to the most exciting available theory. The title, "We Still Don't Know Who Built This Megastructure in Montana," captures the attraction of Sage Wall, but it also contains two assumptions. It calls the formation a megastructure and asks who built it. Neither point has been demonstrated. A more accurate question would be less efficient and considerably less dramatic. Is this large granite formation in Montana entirely natural, partly modified by people, or the remains of an undocumented structure? That version would struggle to fit neatly on a thumbnail, but it describes the real investigation. The word megastructure should be earned through evidence of design and construction. Size alone is not enough. Mountains are large, cliffs are straight in places, and fractured granite can form blocks heavier than anything people have moved. A structure is defined not only by shape, but by intention. Archaeology identifies that intention through context, modification, arrangement, associated materials, and repeated patterns. Until such evidence appears, Sage Wall is best described as a wall-like granite formation rather than a confirmed prehistoric building. This does not mean the site should be ignored. Independent geological mapping would help determine whether its fracture directions match the surrounding batholith. A complete three-dimensional survey could measure how planar the face really is, and whether the apparent courses remain consistent. Geophysics could map underground contacts using several methods rather than one. Carefully selected samples could connect mineral composition with magnetic readings and weathering features. Archaeologists could survey the surrounding ground for cultural material and evaluate the surface marks. Tribal consultation could provide regional context and ensure that claims about prehistoric history are not made without considering the people connected to the landscape. The results should be published in enough detail for outside specialists to review. Protection is also important. While the investigation remains open, visitors should not scrape, chip, clean, climb, or remove pieces from the formation. A modern mark can be mistaken for an ancient one. A moved stone can destroy its archaeological context. Lichen, soil, and weathering surfaces may contain information that disappears when disturbed. Curiosity is useful only when the object of curiosity survives it. Sage Wall has waited through millions of years of geological change and does not need to be improved by someone arriving with a metal brush and a strong theory. The broader lesson extends beyond Montana. Human beings often divide the world into things made by nature and things made by us, but the boundary is not always easy to recognize. Nature can produce repetition, symmetry, straight lines, geometric fractures, and stable arrangements. People can use irregular materials, adapt existing landforms, and build structures that later collapse into something resembling geology. Determining origin requires more than judging which explanation looks right. It requires evidence showing how the object came to be. Sage Wall is valuable because it exposes the tension between visual certainty and physical proof. Many visitors feel sure that they are looking at construction. Geologists can point to natural processes capable of producing every major category of feature. Archaeologists can explain what evidence of building should exist, but has not yet been documented. Property owners and independent researchers continue to collect measurements that they believe may support the megalithic interpretation. None of these groups can settle the question through confidence alone. The geological explanation currently requires fewer unsupported assumptions. It fits the regional setting, provides mechanisms for the large blocks and straight fractures, accounts for partial burial and weathering features, and offers ordinary reasons for mineral and magnetic variation. The artificial explanation remains possible mainly where direct testing has not yet occurred. It could gain strong support through tool marks, prepared foundations, moved blocks, construction debris, secure artifacts, or reliable dating. Without those things, the case remains based primarily on resemblance and interpretation. That conclusion is not the same as saying that Sage Wall has been fully explained. Geology may provide the most likely general origin, while leaving local details unresolved. A natural formation can still be rare. Its fracture geometry may be unusual. Its magnetic properties may differ from nearby exposures. Its relationship with the solstice may be worth measuring. The wall may also have played a role in human activity even if no one built it. A place does not need to be artificial to become culturally important. Perhaps prehistoric travellers noticed the formation long before modern visitors did. Its long face could have served as a landmark. Its shelter, view, or position may have made it useful during movement through the area. People might have stopped beside it, marked it, told stories about it, or used it in ways that left little surviving evidence. These possibilities are modest compared with a lost megalithic complex, but they belong comfortably within what we know about human relationships with distinctive landscapes. Future archaeology may uncover such a history, although it should not be invented in advance. There is something reassuring about allowing the wall to remain uncertain. Not every unusual place needs an immediate identity. The absence of a final answer does not require us to choose the explanation that produces the best story. We can admit that the formation looks built, that geology can explain much of what we see, and that some details still deserve testing. Holding those ideas together is not indecision. It is the correct response when the evidence has not yet separated them completely. So, what does Sage Wall really leave behind after the claims have been examined? It leaves a large granite exposure inside a complex ancient batholith. It leaves intersecting fractures that resemble block boundaries. It leaves protrusions and hollows whose origins have not been demonstrated as artificial. It leaves underground signals that identify material contrasts rather than confirmed architecture. It leaves magnetic variation that may reflect ordinary mineral differences. It leaves a possible solstice relationship that requires independent measurement and archaeological context. It leaves no accepted construction date, no identified builders, and no secure collection of artifacts proving that a megalithic complex once stood there. It also leaves a clear path forward. Map the geology, measure the geometry, compare the nearby outcrops, analyse the marks, repeat the magnetic survey, define the solar alignment, examine the buried contact carefully, search for cultural material without damaging the site. Publish the methods and allow other researchers to test the conclusions. If evidence of human construction exists, that process gives it the best chance of being recognised. If the wall is natural, the same process can explain why this part of the mountain developed such an extraordinary appearance. And now, having walked the length of the granite, looked into its seams, followed the survey lines beneath the soil, watched the winter sun rise beyond it, and considered both forgotten builders and ancient geological forces, we return to the question from the beginning. When you first heard about a massive wall of polygonal granite blocks hidden in Montana, did you imagine a lost civilization? Or did you picture a fractured mountain? Has your answer changed? Perhaps you still see a monument. Perhaps the bolder batholith now feels like the more convincing builder. Perhaps you suspect that the truth may include a natural formation later noticed or modified by people. Any of those reactions can remain open while the evidence is incomplete. The important thing is to keep the observation separate from the conclusion, and to remember that a mystery does not become smaller when we examine it carefully. If you found this investigation calming, interesting, or simply a pleasant way to spend some time among enormous pieces of granite, I would be grateful if you liked the video and subscribe to Just About Earth. You can also share your view of Sage Wall and tell us which piece of evidence you would most like to see tested next. A confirmed tool mark, a foundation trench, a geological fracture map, a complete magnetic survey, or a precise solstice study could each move the discussion in a useful direction. For now, Sage Wall remains where it has been, high in the Montana landscape, surrounded by trees, loose stone, weathered granite, and many unanswered questions. It may never provide the dramatic history some visitors expect. It may yet reveal signs of human activity that have been overlooked. Either way, the formation reminds us that the Earth is capable of producing order without intention, and that people are capable of seeing intention wherever order appears. Sleep well, fellow traveller, wherever you are listening from tonight. The wall will still be there in the morning, and the mountain is in no hurry to explain itself.